on Reddit, questions that
ironically
is
where
ranked
I get
brutal in difficulty, and they use they even say, "Whoa, this is a fairly heavy question. Might be good to skip over," but they're using kinematics when you don't have to use kinematics. You can just use conservation of energy. Whoa, this is a fairly heavy question. Might be good to skip over, but much faster way through a lot of things that I'll be teaching you that you won't be able to get from any other tutor, to be frank. Here are some Reddit guides that I've made and other posts I've made on Reddit, which is
what's up, Harry?
Ironically where I get most of my students. So what can you expect?
Hey, how are you?
Hey, good.
Cool.
I guess like for the next couple times we meet, we can go over. I took the sample test. I did okay. I kind of took it on time because I was visiting friends in DC, so it was kind of off and on. I mean, I was by myself. I just kind of spent all day going through it and really trying to like, I guess, just like make sure I was understanding the questions and analyzing them a little bit.
Mm-hmm.
I did pretty good based on the questions, like the estimated scores around 501. I did really poorly on chem and bio, so I was a little upset about that because I've been working really hard at that.
Mm-hmm.
For cars, it was estimated 128. I got 45 questions right.
That's pretty damn good for cars.
Yeah, but that was pretty good. I missed a couple of like the questions I missed on there were just some of the harder ones, and I reviewed it and I kind of understand where I made my mistakes there. But so far, cars seems to be working really well. That was a big jump because cars has consistently been really low for me.
Yeah.
So I think I figured out just paying attention while I'm reading. I really didn't highlight much, just paid attention where things were, what was going on, and pretty quickly just kind of like eliminated stuff. And I think that's good. Psychology was estimated 127. I was a little disappointed. I got 47 right.
Yeah.
I made sure I wrote down like all of the terms that were in the questions just to kind of like make sure I know all the terms that the AAMC had on there. Even stuff I got right, just making sure I know all that. But chem I got 25 right, estimated 122, and then bio estimated 124. And like, honestly, I feel like I did not understand their chem questions. Like I just didn't get it. Had a lot of weird like stuff on there that I just did not know. And I had a hard time. I reviewed it already, but I guess we can start from the beginning and kind of work through it what we can tonight. I just feel like sometimes they ask stuff that just seems really vague and like not anything I studied. And I'm frustrated because I've taken time to go through content again. I didn't get through all of it. Like, okay, I need to know acids better. Maybe I should know this better. And I feel like it just doesn't pay off. Yeah. And what's frustrating is like, I feel like I could know all this knowledge and I can go in their test day and they test all my weaknesses or my strengths. Like I know they say it's supposed to be your score, but I'm not seeing that. Like I can take a test, I feel like, and get 128 on bio, and I can take another one and get like 122 just depending on what they throw at me. So
yeah, there's a tremendous breadth of material on the test. So, you know, like things that you like really understand that you learn from one practice test might not be like tested again for very long time.
This one was brutal for me. Like this was a hard test. Yeah. All right. I'll go ahead and open it and I'll share my screen.
Okay.
Some things like are frustrating. I also completed all of the. Hopefully we can get through some of this stuff too. Not tonight necessarily, but I did all of the official guide questions. I thought that some of those were really hard. And I did pretty well on those. Like, let's see. I did all of those, and I got log in.
Okay.
Some of those questions, just to me, are just really weird. Like, I don't know. I know some of it's like passage analysis, but sometimes I just don't get it. Yeah, I finished it with about 70% of questions right. Yeah, psychology 70. So psychology, those were hard. 70% chem, 50% biology, 80% right. Cars 73%. So it just nonstop chem and bio seem to be the big challenge here.
Okay.
Yeah, because if I could get those up 4 or 5 points a section, I'd be like in a 511, 514 range. So that's frustrating. And I feel like I'm still not doing my best on psych and cars, but they're going up and they're consistent. So that's good, I think.
That's really good.
And I'm taking as many days off as I can. I'm gonna have a little bit of vacation. At least the week leading up to exam, I'm gonna take the entire week off, so that'll help a little bit.
Yeah, remind me.
I can send you some
as
dates
to-
too. I'll
Yeah.
request some days off work, and I'll send you dates of when I'm off.
Okay.
So maybe we can plan around that and get a lot of time in.
When was your test scheduled for? Again?
It's Saturday, September 11th.
Oh, okay.
Yep.
September 11th.
All right. I will share my screen. And I actually wrote notes. I might want to pull that up on the side somewhere.
Mm-hmm.
I took notes on some of my work stuff. I took notes on things I missed and like why I missed it, just in case that might help me as I go through with you, like my reasoning. Somewhere in here, saved it.
MCAT save your cars document. Oh, I don't know.
I saved it somewhere. I don't know why. Sometimes I open stuff and I need to sample probably. Huh. Go to Finder. I don't know. Hopefully it's saved.
Explanations, MCAT explanations.
I'm not seeing the name. Let me type sample and see. Sometimes might have not saved. Some might have messed up. I had it. Oh well. Let me try it. Just make sure. Oh, here we go. There we go.
Okay.
Yes, I don't know why it's not showing up. Anyway, yeah. I don't know if you can see. Is it too much to keep it like this?
I
I
can.
mean, maybe smaller. I just want to make sure you can see it good.
Mhm.
So I go through it. I mean, I can always open it back later or something,
Sure.
but that might. Can you see this okay? Or do you need
Yeah.
it to make it full screen?
I can see it.
Okay, I think I had. Yeah, that was easy. I know with them, some of the questions seem really straightforward, easy, and some of them I get stuck on.
Mm-hmm.
Yeah, I made a mistake on this one with the stereoisomers, and like I knew the formula and everything, and I still got it wrong. And I think I wrote on here because I didn't realize where I got stuck at in counting them is I didn't realize the nitrogens don't count as a stereoisomer or stereocenter. I mean,
Yeah. You're gonna look for like a carbon that's attached to 4 different things.
yeah, and I guess I didn't realize like
Mm-hmm.
you don't count the nitrogens. Like I saw some people were like questioning that, but like I guess for AMC purposes, you never count. Like I know you don't count double bonds, but I didn't understand why. Like this is something different on both sides here, and there could be a hydrogen.
Yeah.
So I didn't understand why that was a different. It has to be a carbon, I suppose.
Yeah, it has to be carbon.
Okay. I think that's the only reason I got that one wrong. That was kind of easy and I messed it. Yeah, I didn't know how to approach this question. I guess there was something about KSP that I didn't understand exactly.
Yeah. So remember when we went over how all of the capital K stuff refers to the law of mass action?
Sorry, my dogs are like freaking out. So, I knew it was B or D. Like I just memorized like how you set it up or whatever. But I wasn't sure like how you knew if it was greater than, less than.
Okay, so
I guess because they're saying it forms precipitate, and I guess I
Yeah.
wasn't sensing that from the passage. And then, hold on one second. Let's talk about
Sure.
Yeah, so it said something about it because calcium oxalate precipitates
Yeah. So
when the
so
product.
KSP is just So all of the K stuff, if it's a capital K, it's going to be the law of mass action, which is basically the products over the reactants, right?
Yeah, I'm with you there.
Okay, so okay, you were able to cross out A and C, so that's good. So they're saying that kidney stones basically make this calcium oxalate thing, which is basically like a precipitate. And if it's a precipitate, it's not going to be soluble, right?
How was I supposed to know that it formed precipitate, I guess? Was that the passage?
Just from like it says a kidney stone, right?
Oh, okay.
So that's going to be a solid, right? And it says one of the main side effects of prolonged use of compound 1 is the formation of kidney stones, and they're composed of calcium oxalate, right? Which is calcium.
Yeah, I see that. Yeah, so it formed a solid, or that's the precipitate.
Yeah. So basically, all right. So yeah, they're asking basically what's going, like why do kidney stones form in some individuals treated with compound 1? So if it was equal to KSP, like KSP is just basically like the maximum amount of these ions that can be soluble in whatever the solvent is. And so okay, now if it's greater than the KSP, that means that you're going to have, since these are the products over here, like calcium 2 plus ion and the oxalate ion, the C2O4 2 minus. Those are like the products, right?
Is this kind of like the I'm trying to think now. I don't care what law, whatever. Where like if you have a lot of something, it's going to shift. Like what's the
Le Chatelier?
Yeah, is this Le Chatelier's principle? Like if you have solid, like which way it's going to shift, the equilibrium or whatnot.
Kind of, because sometimes there's going to be like Q, which is like the reaction quotient, and K, which is like for equilibrium. So Q is basically like what it would be. So like let's say you started off with something, it's Q, and if Q is greater than K, it means that there's an excess amount of products, and so it's going to shift backwards to make fewer products and more reactants. And if Q is less than K, that means that there isn't enough product. And so it's going to be shifted. Le Chatelier's principle is going to have it shift forwards. So basically basically, since we're going to have calcium oxalate as a precipitate, you're going to basically have an excess of the product. Because what we have here, the reason that we don't have anything in the denominator, like normally we would have the reactants in the denominator, but the reason that we don't is because the reactant is the precipitate itself, and we don't include that.
Okay.
Like this reaction, like if you were to think of it as like a regular chemical reaction, it's going to be calcium oxalate, like CaC2O4, like solid.
Okay.
And then, an arrow, that's like the reactant, and then, it will yield calcium 2 plus ion, like aqueous, plus the oxalate ion, aqueous. Like that'll be the chemical reaction.
So is the reason, so we have precipitate left over, is that the reason why the reaction's greater than KSP?
So if you think about it, so these are just the products, right? On the product side of the chemical reaction?
Yeah.
So, okay, if there's an excess of product, Le Chatelier's principle will dictate that it's going to be shifted backwards to favor the reverse reaction, which is the formation of the calcium oxalate precipitate.
So gotcha. So in this case, since there was more product, it's going to shift left back to the reactant side.
Yeah.
I guess the problem I had with this is I understand Le Chatelier's principle. I've never really understood fully KSP that well. And I guess I had a hard time deciphering that from the sentence right here that there was a precipitate.
Yeah.
So is a precipitate just something that's left over because why?
Oh, the precipitate is just it's going to be a solid, right? And basically, when you're dealing with solubility, if something is soluble, right, it's going to be like mixed in with the solvent. It won't be a solid. If it's not soluble, that means it's going to be a solid, right?
So yeah, so like some things are really soluble and some like are not as much. So like this has a lot of precipitate left in it, I guess.
Yes.
I mean, that's kind of clinically what they were saying based on the question. I just wasn't thinking of it in terms of like just straight Gen Chem. Yeah. It kind of got me to thinking about something else I was going to ask. I losing my train of thought. I was thinking about the solids. Oh well.
Yeah,
I think I understand that. It was just kind of hard for me to decipher from that sentence right away what they were saying, and I was kind of like, what do I do? Like, I knew these reactions were incorrectly like expressed, so I knew these were right, but I just didn't know which way it was. So basically,
yeah, and in your
since it favored products, it's going to shift to the reactant side, which means the KSP is less than. I guess it's kind of hard for me to visualize in my head KSP being less than. This is why I always remembered stuff for chem, because I just did not understand it that well.
Yeah. So basically, like, first of all, like, all right, so in your notebook, I kind of there's like a section where I go over solubility and basically KSP, which is a solubility product, and how that differs from the molar solubility. So it's essentially, KSP is basically the equilibrium constant for something that's soluble, right? So if something is equal to KSP, that means that it's perfect. It's not going to do any Le Chatelier's stuff.
Okay, so I just look at this way and I'm thinking that it's saying, is this expression saying that it favors the products? Is that what this is saying?
Yeah. Because
so it's easier for me to look at it that way.
Yeah. Because like everything goes back to the law of mass action, right? Which is basically like let's say you have a chemical reaction, right? You have the products as the numerator, and then the reactants as the denominator.
Okay.
And like, if there's like two calcium ions like in the balanced equation, then that 2 turns into like the exponent.
Yep.
Yeah. So now there's like a capital Q, which is essentially the reaction quotient, which is just like how it is for a reaction. And relative to the equilibrium, it's going to be either going like shifting towards the forward reaction or towards the reverse reaction. So even though they're not talking about Q, we're basically dealing with something that isn't the equilibrium constant for solubility. So basically, if the product concentration, like for B, that thing on the left, like the concentration of calcium ion and the concentration of oxalate ion, that can be thought of as Q. And if Q is greater than KSP, that means that there's an excess amount of product. Okay. Excess amount of product. So it's going, in order for it to go back to equilibrium, it's going to have to reduce the amount of product. So it's going to, the reaction is going to be, it's going to favor the reverse reaction.
Yeah, so if you have a lot of, you have to have a lot of product for it to want to reverse the other way, basically.
Exactly.
That makes sense. And I
D
understand
is
the law. I guess I
opposite.
just don't understand. I didn't understand how to express it in terms of KSP that well. I mean, I kind of knew what was going on with these two, but I didn't know how to express. I guess I didn't know what this meant exactly, so I didn't know which way to go. So I had to guess.
Yeah, so that's essentially, just think of it as like the equilibrium constant for solubility, aka like the perfect amount of product and reactant in order for everything to be perfectly soluble.
Okay, so because there was the precipitate, I'm trying to understand that though. So I understand it's basically a efficient like reaction, and we're getting all this product, and I guess that means since we have precipitate, it's because we have a lot of product, or is that just because it's not being fully dissolved?
Yes. Because this entire thing, it's greater than the KSP. It needs to be equal to the KSP in order for it to be completely dissolved. And so in order for, if it's greater, right, it's going to have to go in the reverse direction to become a smaller number for it to be equal to KSP. So it's going to basically create some of the calcium oxalate precipitate, just enough for it to be, for the ratio of this to be equal to KSP.
Okay, so like in what situation, I guess, is it the reverse of that? I mean, I understand like if we didn't have a lot of reactant, then we're not going to get much product. So that would, I guess.
So if you look at D, that would be the reverse, because that's saying that there isn't enough product, because that is, it's less than the KSP. So it's saying that it's not enough product, so it's going to push, it's going to the reaction is going to be pushed towards or favor the forward reaction, which means that more reactants must be made. So D involves it going in the forward direction, whereas B involves it going in the reverse.
So I understand it in terms of like, if we have X amount, we're going to go shift right, or if we have this, we're going to shift left, and what equilibrium is. I guess I was a little confused now. Like, I guess I just think of precipitate as something that happens in lab, and that's where you form a little bit of that solids or whatever. It doesn't completely dissolve. So now I'm trying to like relate the precipitate to like why the answer is the answer now. Like, I understand if you have a lot of something, you're going to shift, right, form more product. If you don't have a lot of reactant, if you have a lot of product, yes, you shift the other way. So I guess I'm trying to understand now the whole precipitate situation.
Yeah. So like, think about like when it equals KSP, right? When it equals KSP, that means that all of that precipitate has dissolved. Okay.
So like, that's some more, I guess, would you say that's, I guess it's more efficient of a reaction?
That's just,
it's fully dissolved?
Yeah, so that's just going to be at equilibrium right there.
So if we have, I'm just trying to make sure I understand this in terms of precipitate, just to make sure I got this right. So like, if we have a lot of, not necessarily, I guess, there's different ways to express this in terms of like what they're testing, but like, if you have precipitate left over, does that mean for sure you have a lot of products? Like, I just want to make sure I understand every exception.
Generally, okay, wait, what was your question again? Say that again.
All right. Yeah, so I understand that we're forming a lot of products here, right? We're forming products, and they said there was, all right, I guess you could infer there was precipitate because of the calcium, the kidney stones being formed. So since there's precipitate, we know it's not at equilibrium. And in terms of like relating the expression, I'm just trying to make sure I understand why we know which way it's the air, like it's facing. Like, I understand. So you're saying there's a lot of product. Are we just saying, since this is a favorable reaction, that we're favoring the product? But I'm not trying to overthink. I was trying to understand it in terms of the precipitate. I'm probably way overthinking this, but I'm just trying to make sure I got it.
Yeah, let me see if let me see something for a sec. If I can find something that would, I'm gonna look up reaction quotient.
Yeah, their answer explanations are never very good.
Yeah. So here, copy image address. So I'm gonna I put it in the chat, so you can click on that. So here, yeah, so this is what I was talking about with Q, right? So Q is just the reaction quotient. Basically, not when it's at equilibrium, but you always compare it to equilibrium. So when Q, right, is greater than K, all right, it's going to move backwards. The net reaction is going to move to the left because you have too much of the product.
Gotcha.
And when Q is less than K, you have too much of the reactant, so it's going to move to the right. And it's going to do that until it reaches equilibrium, which is when Q is equal to K. Then there's no net reaction.
Gotcha.
So that is, and then here, let me show you this. So this other link picture over here is what I talk about when I talk about the law of mass action, because everything with a capital K relates to the law of mass action. So, like, here we go. So, like, see, this is a chemical reaction over here where little a and little b are, like, the coefficients, like a number, like 1 or 2 or something like that, right?
Yeah.
So, basically, like, it comes down to this. Like, you put the products first, like, you know, concentration of C, and then, you know, that coefficient becomes the exponent. And so you see how it's a reactant. Products on the top, reactants on the bottom.
Yep. So that's Q.
Yeah, and then you see how, and then Q, if it's greater than K, the reaction forms the reactants. So in that question, like the thing on the left, the reactants is calcium oxalate, like solid.
Mm-hmm.
And the thing on the right, the products are going to be calcium. Yeah. So since if it's greater than K, the reaction forms a reactant. So in that question, the reactant was the precipitate. So it's going to form that.
Okay, that makes more sense. I think I was a little bit overanalyzing. I didn't understand part of that, so that makes more sense. Okay.
Yeah.
Oh, I got this question. I thought this was kind of stupid. So, channel X transmits only the small substances dissolved in the extracellular fluid through the axial membrane. Which substance does channel X transmit? And they said the answer was sodium ions, but I got confused on this, and a lot of other people said the same thing on Reddit. So let me see what I wrote here real quick.
Oh yeah, you could just look at the periodic table and then you'd see that.
Yeah, I did that, and I think I was confusing the difference between atomic radius and the molecule size. Because I went with chloride because it's smaller.
Chloride, okay.
I wasn't sure how you knew what they were asking, whether they were asking about ionic radius versus...
So check this out. So, well, yeah, because they're saying ions. So, okay, you have the right reasoning in that... Well, okay, so think of it this way. Like, atomic radius is in the middle, all right? Now, a cation, right, means that it loses an electron or two. So that means that the protons in the nucleus that pull, like, everything, you know, because the protons in the nucleus pull the electrons inwards, like, towards the nucleus, right? Because they're oppositely charged and they're, you know, attract. So basically, whenever you lose electrons, that pull from the nucleus, like, it will pull it even further in. It's almost like let's say, like, there's 2 electrons and you have, or let's say, like, you're doing, like, a workout or something with, like, cables.
Yeah.
And, you know, a cable is attached to 2 different weights, and you're pulling that. And then imagine, like, one of the weights is gone, which means, like, an electron is gone. When you pull it, you're gonna be able to pull it closer to you. So, yeah. So cations are always gonna be smaller.
Gotcha. And I sort of knew that, but I guess I got tricked up by the question because I was like, I knew what I knew, I had memorized, like, I know this. Like, I had this memorized because I've had questions come up about it. And I guess I didn't know based off of the question. I guess I should have seen where it said, but it didn't say ions though in the question. That's, like, I mean, it goes down here.
Mm-hmm. So this is how I would do this.
That's why I didn't know if it was ionic radius or atomic, and I guess I was like, oh, well, okay, well, if I go this way, it's has a smaller atomic radius, and I guess they meant ionic radius, and that's why I had it wrong.
Yeah. So first of all, like, yeah, you were able to cross out proteins because those are huge, and then for sodium, potassium, chloride, they're all ions, right?
Yeah.
So that means sodium is going to be a cation, potassium is a cation, chloride is an anion. So when you're comparing them, just always try to remember that like what I draw is like kind of like maybe like cation and then like a less than symbol and then just neutral atom and then less than symbol and then the greatest one is the anion size. Because with an anion...
I guess, does that have to do with the cations giving up the electron is why with the size?
Mm-hmm.
It's smaller?
Yeah. Does it make sense that the nucleus pulls the electrons towards itself?
Yeah.
Yeah. So now imagine
I just got it absolutely stuck in my head that they were asking about this.
well, yeah. That's like
I know there's a difference. Like, I mean, I've memorized most of those periodic trends, and I usually get them right, so I was kind of pissed off. But I kept reading it, like, is that what they're asking about? And I guess I misunderstood.
Yeah. So yeah, it's the ion stuff. But
yeah,
like,
so
do you
so going
understand
back,
why...
like, I'm just like want to make sure how. I guess like I just because they didn't say it in the question exactly, unless I'm just like not understanding. Like,
well, in the choices
atomic
they say
versus ionic
ions,
radius.
right? Like sodium ions, potassium ions, chloride ions.
I'm trying to. I guess I'm trying to think of when I came across a question that was like that, where they meant the atomic radius. I guess maybe they would have been a little bit more straightforward with that, like in terms of like the molecule or like I guess size.
Yeah, because like we're usually going to be dealing with the ions if they're dissolved, right?
Yeah.
Because we're in the body, which is mostly water, right? It's gonna like break apart into like it's gonna dissociate. You're not gonna have like solid sodium and stuff, right?
Yeah.
Like
Okay.
like salt, table salt is like NaCl, right?
Yep.
And then in water that turns into sodium cation and chloride anion. But does it make sense that anions are larger?
I guess in terms of that they are going to want to pull off and hold on to electrons.
Yeah. So like let's say it's...
I think of it that way. I understand that. I guess I was so stuck with that table here, and I wasn't thinking of it. I was thinking in terms of, oh, I memorized this. That's what they're asking in terms of what they meant with the whole ionic radius. So I see that now. So I'll just pay attention to the solution if they don't explicitly state it in the question. Just being a little more careful reading the question if they're asking, like making sure I know atomic versus ionic radius.
Yeah.
Because that makes sense the way you said it. I just memorized the table, like the trends I know. Yeah.
So, like conceptually is always like the best route to take.
Yeah. All right. I was just a little frustrating that I got it wrong because, like, I knew what I was talking about, but I was wrong with what they were asking. So it's all right. That makes sense, though. I understand.
Yeah.
Yeah, I got this question wrong, and I immediately knew it was Ohm's law.
Yeah.
So I'm noticing I am a little weak with physics. I'm going to make sure I do the entire physics Q pack for whatever reason, conceptually, I have a hard time with physics.
Yeah. Most students do, and like one of the things that I recommend students to do is like to get out of the mindset of memorizing things is to just play around with like the units and things like that to see like how you know what the things are. Like for instance, like so okay, for instance, they're asking for current, right? What's the unit for current?
Isn't that amperes or whatever?
And what's that equal to?
I have no idea.
So see, that's what I mean. So like knowing that is going to help you a great deal. Now, so let's figure that out, right? So current is basically it's like the rate at which a charge moves. Like when you measure like a current in like a wire, right? It's like electrons that are moving per some time. So an amp is basically going to be in coulombs per second. So being able to break down the things into their SI units are going to help you. So coulombs per second is what you need to find, right? So you're going to need to basically find out how to get that, right?
Mm-hmm.
Now, voltage. What do you think about voltage?
Isn't it charge?
So like it's like another way of talking about energy. And when you think about energy, what unit do you think about? Think about like so like potential energy, like MGH, right?
Okay.
So that's like kilograms times acceleration times like a length. Or how about, let me put it this way. So power is in watts, right?
Yep.
So what's a watt?
Isn't it? Hold on.
Mm-hmm.
I was what you just asked me. Hold on. I don't know why I'm missing the units today. I can't remember. I could have told you.
Okay. I'm gonna just tell you it's joules.
That's it. Yeah, joules.
Okay. Now, what's the formula for work?
Work is force times distance.
All right. So, what's the unit for force?
Isn't it Newton meters or something? Newton.
It's newtons, and distance is just meters. So newtons times meters is equal to a joule.
Okay.
Okay. So okay. Voltage then is going to be joules per coulomb. So if you do Ohm's law, right? Where you could do whatever. So they're doing V over R. So basically they're doing like joules per coulomb divided by something to give you coulombs per second.
Gotcha. And I, in fact, I wrote this on my paper, but I didn't know what it meant because
because a lot of people just know it like at current as amps, but the key here is knowing how to break it down into the SI units.
Okay, so I honest to God hate physics and I don't care. So is there a cheat sheet or something I can practice this on and just Because I always get stumped by this crap over and over again. Yeah. And I never memorized, I memorized all my formulas, but I never memorized what they meant. Mm-hmm. I just did enough practice problems in physics where I would get the answer and I didn't keep track of my units, and I just knew that I would arrive at the right units if I did all the steps.
Yeah.
It's bad, but that's how I learned physics, and I know a lot of people who learned it that way.
Yeah,
But it doesn't work on the MCAT because
Remem-
it's more conceptual.
yeah. Remember that physics mindset thing I shared with you?
Yeah.
Yeah. So the physics mindset, like the problem that is here for that is, so this is like how I was taught. So it says, imagine you have a mass m, a length h, a velocity v, and acceleration g. What combinations of these can you make that will have units of time, force, energy? So I'll have like these types of questions for you, because this type of question, like, it's not like with physics, like the idea that most people have with physics is just like, just tell me like what the values are, I'll plug it in and I'll be done. But the MCAT is not going to just be plug and chug. They're not going to be for the person who just memorizes the formulas. They're going to be for the person who can like think in a, flexibly. Like,
You know what pisses me off though is intro to physics in college is more conceptual, and that would have helped more with this than me actually taking regular physics. Because I just did plug and chug.
Yeah.
It's really frustrating the way they're doing this, and I mean, maybe it's the school I went to, but everybody I know who took physics anywhere, if you just did the problems, you were good to go. So it's just irritating that I've had to like relearn this. And I mean, I like physics, I just didn't like it that much to learn this. But it's all good.
So I'll have you do like questions like that. But like, for instance, right? Let's look at these, different types of choices, like what like units they have, right?
So on this, I did arrive at this, and I was thinking about what these meant. So,
yes.
And I went back to, I knew that, I want to make sure I have this right. I knew that we weren't talking about radius here. Was I right to assume that?
Well,
because I knew the units had nothing to do with radius in terms of like axon potential or whatever we were talking about with the pulse.
Yeah. Well, we're gonna still need like, so radius and length, they're both gonna be like a distance, and we're definitely gonna need that. It's just what is going to be like, which one do we use, right? Because radius is like for cross-sectional area and stuff. So like, okay, so let's check this out for a sec. So like, potential we know is going to be joules per coulomb, right?
Yeah, I didn't know that. So.
Yeah. So I'll like make some questions like this for you. Where
I didn't know what any of this stuff really means, to be honest. Like just kind of like generally, but I didn't know the potential mattered here. Like, I was just looking at the formula. I'm like, okay, I need this over this to get current. I knew the I is amperes, but I didn't know what that meant.
Yeah.
So I was kind of SOL.
All right, so check this out, right? So okay, potential, that's V, right? So we need that, right?
So joules per coulomb is V, and that's potential.
Yes. So and then for resistance, maybe we don't have to turn that into SI units, because you know what? D has resistance per unit length and then length.
Okay.
From those two, how do you get resistance?
I can't remember.
It's not about remembering. Just think about it. So like, in terms of like math, like what is like resistance per unit length? What does that mean? Like the per part, what does that mean?
Not really sure.
So if I said, whatever, a bottle of water costs $1 per 12 ounces. So like, that per means divide.
Okay.
Like if I said a bottle of water is $1 per 12 ounces, then when you divide that, it'll just be like 1 over 12. Do you remember what that was? 1 over 12?
Nope.
Okay, so that one's useful because it ends up being equal to
Oh,
the
point.
R.
Is that the one that equals the
Yeah.
point? Wait, yeah. Okay, I know it then. 0.08.
Yeah. So if a bottle of water costs $1 for a 12 fluid ounce bottle, how much does it cost for an ounce? It's just 1/12, right? So 0.08. So basically 8 cents per ounce, right? So okay. Now, let's say that when they say unit length, that means like it's 1. So like, let's go backwards and say it costs 8 cents per ounce of water, right? Now, how can we get that top part there? So here, maybe I should write this down, but when it says resistance per unit length, I would just write resistance over length, right? Do you see that?
What are you writing on?
Oh no! Sorry. I haven't written it down yet. But
Okay.
I was just saying, like, resistance per unit length. You would write down resistance.
Oh yeah, no, I visualized that's with the division. Yeah, I know what you're saying.
Divided by length, right?
I didn't pick this answer for one. First of all, I didn't know the potential part, and that's why I got A wrong too. But I wasn't sure if it was like I didn't know what that meant. I just assumed I knew R was resistance.
Yeah.
I even know what resistivity, if that was even the right.
Oh yeah, so that's a little different. But check this out. So if you could imagine resistance divided by length, right? And we need to find out the resistance. How can we find it out from resistance over length? Like, what can we multiply that by to get resistance? So here in the chat, maybe I'll write it down. So like, resistance over length, like here, this over length, right?
Mm-hmm.
So let's say we can multiply it by something to get just R. What can we multiply it by? Because we have resistance over length, right? Do you see that?
Equal the current, right?
Oh, so don't worry about that for a sec.
Okay.
Because we're just trying to find resistance, so we can plug it into that formula. So like, if we have resistance per divided by length, how do we get just resistance? How do we get rid of that length in the bottom?
I have no idea.
Well, think about it. Like, all right, if I had 1/2.
Oh, by multiplying length to the other.
Yes. So resistance over length times length gives you resistance.
Okay.
So basically, that's R, right? And then potential is just V. So basically D, so it gives you potential, which is V. And then resistance per unit length, if you multiply that by length, you get resistance. So then you get R. And then you divide V divided by R to get current. What do you think?
It makes a little bit more sense. Like, I honestly just didn't know what any of these units meant, like, for the most part. So I never learned that when I took physics. Like,
What?
I
Wait,
think
which
I should get a
part?
refund for my money.
Wait, which part?
Just like, I just didn't understand any of the units.
Okay.
Like, I mean, like, when I took physics, like, I just didn't really, I mean, I kind of was familiar with them for certain problems.
Yeah. So
like-
you know, I don't worry too much about like the coulombs per second thing. I'll make some questions for you, like custom for that. Because for this one, you still don't necessarily need to know that. But you just need to see how.
I just
Like-
didn't see. So
Yeah.
I understand the potential now.
Mm-hmm.
That's the Coulomb. That's the the volt. That's the V is
Yep.
the Coulomb or whatever.
Yep.
Charge
Mhm.
Q or whatever.
Yep.
And the resistance, I guess I wasn't sure. Like, I just know of R in my head. That's just resistance. So like,
Yeah.
I didn't know how to go about that. And you're saying it's resistance over length,
Yep.
but you're multiplying it by length.
To get resistance.
But why are we saying and length here?
So these are the 3 bits of information that they're asking what information do we need in order to find the current, right? So we need the voltage and we need the resistance, right?
Yep.
And like D has potential, so that's the voltage, right?
Gotcha.
And then resistance per unit length, and then length. So all we do is multiply resistance per unit length by length. The lengths cancel out.
Oh, I see that now. I didn't see that. Okay, I see that now. Okay.
Yeah. And if you
And that's-
wanted to know what resistivity is, it's resistance is equal to, it's like the Greek symbol rho, which kind of looks like a P, which is resistivity, times length over cross-sectional area. So resistivity is that P that I wrote down, and that's just something that's inherent in whatever material you're using. And then conductivity is the inverse of resistivity, which is 1 over like rho, which is P. So yeah, so that's what those things are.
I was like, well, up here it says a nerve
Uh-huh.
conduction. I'm like, okay, here we go.
Yeah, but like, you have the right idea with Ohm's law, and then it just comes down to how do you get the the V and the R.
Yeah, I didn't know what those units meant. So now I know what this one and what that means. I just didn't know.
Mhm.
That's not. I don't know, but like, yeah, it's a little frustrating. I get a lot of that stuff wrong.
Yeah. So I'll make some questions for you that are like very customized, because like you just need to be comfortable with manipulating equations and formula and stuff like that.
Yeah, that would definitely make me more comfortable on the test too. I mean, some of the certain types I get right, but yeah. This question, let me find it. Make sure it's number 11. Okay, there was a reason I got this one wrong. Let me understand. I knew right away it was going to be B or D, but there was a reason I went with. Wait. Yeah, it was a weak acid. Okay. I said it was a strong base, and there was a reason I said that. Let me read why I picked that.
Mm-hmm.
Okay, so the passage said completely dissolves in water, and it made me immediately think strong acid. That's why I picked that almost right away, because I was having a little bit of a tough time getting through this stuff, but it said,
Don't get too used to that, because remember we were working on the Control F in your head.
yeah, I know. I was trying to get through it.
Yeah.
It said in the passage somewhere that it was strong. I'm trying to remember where it was. And it threw me off because I was reading it.
Uh-huh.
Oh, here. The compound completely dissolved in water and weakly conducted electricity. I was missing this part, apparently. I think would have helped, but I guess I assumed something that completely dissolves in water was a strong acid, usually, right? Like, I mean,
Yeah, I see what you're saying. I think
that's the case, and I saw other people on Reddit that were getting it wrong for that reason too. And the answer was it was a weak acid. And they're saying, I guess I should have known here. Like, I even did the pH calculation right on another question, And apparently, since it wasn't below 5, it wasn't a strong acid. So yeah.
Well, yeah. Strong acids are going to be like way, way, way lower pH. But no, this is tricky because it does say completely dissolved in water.
And I identified it was an acid, and I was frustrated because I guess I should have thought of that, but their wording of that question was kind of dumb because like they said it completely dissolved, and generally strong acids fully dissociate. So like I knew a concept and I got it wrong because of the way they worded it. Like if I went back and did it again, if I didn't, I would have had to pay extra attention to this pH is 5, and I knew that wasn't a strong acid.
Yeah.
So I was, that sucks. So
let me
like
see
I don't know.
Let me see the top of this
how else
for
I
a
would have
sec.
gotten to that.
Let me see the top of this passage for a sec. Let's see. Okay, so this is how you'll do it. See how it says hydrated oxides?
Okay.
Do you see where it says buffering agents?
Yeah. I was thinking of, when I saw that, I was thinking of like the, like buffers, resist changes, and...
Yeah, and what are buffers? Like, they're basically weak...
weak acids, right?
Yeah, weak acid or a weak base, right?
Man, I should have thought of that. But I did read that initially, I think.
Yeah, so they start off by saying...
I was also trying to go up to the unknown... I guess I was trying to quickly skim because it said unknown compound.
Yep.
And I don't think it talks about that up here. So I was like just skimming through. I'm like, okay. And I was like trying to find... And it's that, that's why I got right to here. That's why I didn't go back up here. So that's what sucks is like I'm trying to get through a test with reasonable time. And like if I had read the first sentence, that helps. But this did contain what they were talking about. Yeah. And then that was misleading. So like that's something that I would get wrong on a test, and that frustrates me. And I did know the concept pretty well. But I guess I would have had to use something that it didn't say. That's kind of frustrating. So like when you're going through it quick like that, what would you do? Like, I guess I could go back and read more, but you don't have that much time. That's why I try to hunt really quick. I'm like, okay, boom, that's an obvious statement. That usually means that. And I think I made way too strong an assumption. But I think there were multiple. You could have used this to get to it. You could have also used this. That was 2 ways.
And
I
then
stuck
weakly
with this way, and I went
electricity.
right away to it. Say what?
Oh, and then the part where it says weakly conducts electricity.
Yeah, I wasn't sure what that meant exactly.
So like, when things break apart, they break apart into ions, and ions enable it to conduct electricity. Like Gatorade and stuff, like electrolytes.
Yep.
Those are just ions. Electrolytes like make it possible for there to be an electric current. Like if you're dehydrated, like let's say like you're out in the desert or something and you're completely dehydrated, the first thing that happens is you lose like motor function because your nerves can't conduct electricity because they need an electrolyte kind of solution. So that's why you need to get your salts like that.
Okay. And they even said in here though they didn't even. It's obviously them, but they didn't talk about the top part. But I see there's like 2 ways to get it. It's just frustrating because like I was on the right track and I got it wrong. Because they suck.
Yeah, no, the completely dissolved part definitely.
I was just, why would they put something like that in there? That's what frustrates me with them.
Because
like,
otherwise everyone will get it right.
Yeah, some other questions are ridiculous. But okay. I got this one wrong, and I did not really understand this well. 2 additional compounds were studied. The NO2OH dissolved in water produced an acidic solution, and IOH2 dissolved only in acid. What type of compounds were these? I really didn't know much about oxyacids and bases, but I was just like, okay, we'll just stick to what you know about acid base.
Yeah, I think they talk about it like in the top, because this entire thing is about oxyacids, right? They're saying oxyacids are bases, right? So you can determine that based on, let's see. So A is a central atom, M is either 0 or a positive integer, and N is a positive integer for either oxyacids or bases. So let's see. That is for sulfuric acid, and then this is for calcium hydroxide. And then they say that, okay, if the central atom A is an alkali or alkaline earth metal, compound is basic. But if it's a non-metal, it's acidic. That's what's going to give you the answer. So NO2 is a non-metal, so that's an acid. And nickel is a metal. It's a transition metal, but it's still going to be a metal, so that should be a base.
Okay, well, my reasoning here, I guess, was like dissolves like. So that's how I got to this answer, or whatever.
Uh-huh.
Because it said NO2, OH dissolved in water and produce an acidic solution, and NiO2. So I was thinking of the concept like dissolves like, which maybe that's not. Somebody else said they didn't know the same thing.
Oh,
But-
yeah. That's only for, like, if it's polar, it's going to be dissolved in a polar solvent. And if it's non-polar, it's going to be dissolved in a non-polar solvent. But this is what's going to help you get the answer. So, okay. If the second thing dissolved only in an acidic solution, that means that it basically requires an environment which makes its base properties pretty much stand out. So like in other words, so like a base would have a pKa where the pKa is going to be greater than the pH of the environment that it's in. So it's going to be in an acidic environment. So that's why they're saying, it's insoluble in neutral water, but it'll dissolve if the solution is acidic. So it's actually going to be like almost the opposite. It's actually the opposite of like dissolves like when you're dealing with
that's why I got it wrong.
acid when you're dealing with acids and bases, because in order for an acid to behave like an acid, it needs to be in an environment that is relative to itself more basic. But if you didn't, know that part, you could just look at the central atom, and if it's a non-metal, it's going to be the acid. If it's a metal, it's going to be a base.
Oh, that's easier for me because
That's
I've read the acid base chapters a million times. I never understand the way the AAMC and then test the stuff.
Yeah,
like,
this is in the second
it always
paragraph.
throws me off, and I feel like I know what's going on, and I get stuff wrong. I'm quick between like, oh, it's got to be one of these two. Which one is
Yeah.
it? Okay, so you said if it has a.
Yeah, so that's in the passage. So like if you scroll up, I think it's like in the second. Yeah, it's the second thing right there.
I wasn't paying attention to that because I didn't really understand it and I didn't want to waste time. Yeah, so central atom is an alkaline earth model. It's basic, so that actually could help you answer the question.
Yep. Because the NO2 is a non-metal, and that's an acid. And the, nickel one has a metal. So it's a base.
I'm just gonna memorize that because this tripped me up. See, I thought I knew this conceptually and I got it wrong. So
Well, like this
All
isn't
right.
something that they really teach us. That's why they mentioned it in that second paragraph.
yeah. Okay. I guess I need to pay more attention. I got this one wrong. I got confused.
Okay, so it's an acid, right? So it has to be a non-metal. This is like that previous, like what you used to get the right answer for the previous question, you use for this one also.
I guess there's. I'm trying to remember what my reasoning was for here. I'm gonna go over to the side. Oh, I think I was thinking of just the weakly conductive electricity part.
Uh-huh.
And I guess I was thinking, that's why I actually think this was wrong. I thought transition metals didn't conduct much electricity. They weren't like that great, but I think I was thinking of non-metals. I don't know why. I could have answered it that way. I knew it wasn't a noble gas. And I knew it wasn't these two because these are pretty good conductors, right? Alkaline earth metals. So that had me between these two.
Yeah,
And
metals in
For
general.
some reason,
yeah.
I got it stuck in my head that certain transition metals weren't that good at conducting electricity. But I should have said non-metal. Like, you could have gotten it that way too.
Yeah.
That was kind of testing a basic concept. For some reason I got it stuck in my head that certain transition metals weren't that conductive, which I think is true. There are certain ones.
There's
I think
different. Metals have different, conductivities. Kind of like the previous passage or whatever, conductivity, which is, it's innate for whatever type of metal you're using, but, metals can be, like, a metal, the least conductive metal is still going to be more conductive than a non-metal.
Okay.
Like a metal can be the least conductive, but it's still going to be more conductive than a non-metal.
Okay. Yeah.
Yeah, how was that squalene one?
This one.
Yeah. Oh yeah. Oh, nice. You got that. Yeah.
Yeah, I didn't have any trouble recognizing. I knew that would make a steroid.
So like, what would it make that makes the steroid ones? Cholesterol, right?
The 5 rings is how I knew, because I knew if cholesterol was a 5 ring.
Yep. Good.
Yeah. And I think I knew what the squalene is a prerequisite or something.
Mm-hmm.
I knew it wasn't phospholipids, and
Yeah.
I knew it was. Yeah, I just knew the concept, I think.
Yep.
Yeah. This question I guessed on. I really did not know what the hell they were talking about here. I kind of know monosaccharides and disaccharides a little bit. They were like,
oh, this is asking if it's a reducing sugar or not.
yeah, I don't really know that stuff that well. Does that have to do with anomeric carbon or something?
No, it has to do with whether or not it's an acetal or a hemiacetal.
Yeah, I never learned that in Orgo. I didn't learn it now.
Yeah, I think.
I remember what my reasoning was for getting this right. I looked at all of them. There was a way I got this right. Let me look. That's why I took notes. What number was this? 16. Oh, I actually said this made no sense. Yeah, I guessed on this one.
Yeah, this is a.
Oh, I picked this one. This is why I picked this one, because I saw the. I guess the sucrose was the only one that was like really drastically different. So
Yeah.
that's why I went.
That's always a good strategy.
They all look pretty much the same. I was like, there's nothing structurally that different from those 3, so I figured it had to have been D. That's the only reason I got it.
Yeah, I'm gonna see if. Yeah, that thing is. I'm gonna see if I have anything for, whatever. I'll check later.
Okay. Yeah.
For,
Sometimes with them they ask really random stuff like this that like. Some of these are time killers. Like this, I kind of picked it and moved on, but some of their questions can be time killers. Like there were some in here that were.
Oh, okay, I found the thing. So, so a reducing sugar is an aldose. Non-reducing is a ketose. Let's see what I wrote. Sugars with greater than or equal to 5 carbons prefer a ring form, and it forms either a hemiacetal or a hemiketal. And the hemi ones are reducing. The acetals and ketals are non-reducing. So basically, so like this thing over here is like a test for reducing sugars.
Mm-hmm.
So we're gonna just look for something that isn't reducing. So, like a hemiacetal, hemiketal, they basically involve like an OH group, like one carbon with an OH group attached to it, like an R group, and then like the oxygen attached to like something else. So if you look at, let's see, D, yeah, okay. I didn't even biomolecules here. I'll see if I can just add this or share that with. Well, actually, it might already be there, but I'll share something with you for these, because this is kind of annoying. It goes into like you have to know like a hemiketal, hemiacetal, and then
Yeah, and I even
acetal
tried
stuff.
going through that reactions. I went through and tried memorizing it. It's just like I can never remember what they look like structurally. So I was trying to understand what they are. I don't know. It's kind of like one of those random orgo topics.
Yeah, they're
But-
pretty hard to kind of notice. I always thought they were pretty annoying.
Yeah,
But
I mean, you really don't get a whole
did a
lot of.
good
I mean, I didn't get this
strategy.
in biochem. We didn't really cover that in depth with sugars.
Yeah, it's gonna be the one that you chose because of that. Yeah.
I mean, I don't know.
Yeah. See how that.
Would the ring make it more stable or something too? I don't know if that's anything to do with it.
So here, I'm gonna share my screen for a sec.
Okay.
All right. Can you see it?
Yeah.
Okay, so carbohydrates must have an okay, so blah blah blah. But look, so basically, like, okay, so this is like a hemiacetal, this is like a hemiketal, and basically what that means is, so like hemiacetal, like, you know, has an H attached to it, R group, OH, and then like an oxygen attached to like another R group, so that could be like in a ring, for instance. This is a hemiketal, which is the same exact thing, except that hydrogen is just another R group. Now, let's say, so like basically that OH group is what gives it away. If that OH group turns into another O attached to R stuff, right, for both of these, then it becomes, for in this case, it's an acetal, in this case, it's a ketal. So that's what we're basically looking for. So just like these kind of structures.
Yeah, and I like seen that before. I just have a hard time visualizing it when it comes to real questions like that.
Yeah, no. So like, okay, so now let me.
You could you could go through almost a whole semester of this crap. Like
Yeah. So go back to sharing your screen, and then we'll you know, see it for the actual thing. So
Cool.
So okay, so like all of these, like, so, you know, I'm just looking at like the bond between like the two whatever sugars, and I see basically so like that first one, let's see, I see like an O. So I'm looking at the carbon for A, like, yeah, that carbon like down there.
You're looking at where you're looking at. You're looking here.
That
Where you're
carbon,
looking?
yeah, right there. So this carbon, right? It's attached
Yeah.
to an H, which, you know, we don't see. It's attached to like an R group, which is just like that crap, and then it's attached to an O, like an OR on like both sides,
Okay.
right?
All right, both. I guess that's an OR group, right?
Yep. Just like
And
with a
then-
different R, right?
Yeah, this one too, right?
Yeah, and it's pretty much the same thing for like the carbon on that other sugar, like on the right, the other side of that bond.
Here.
Oh, like that's still on that bond? Yeah, that one. So that's attached to an H. It's attached to this OR group. It's attached to like an R group over there, another R group, right? So like we basically have that same kind of thing for all of these. Now for sucrose, let's look at how it's different, right? So like it's pretty much the same on that end, but on the carbon that's on that 5, the pentose sugar, yeah. So this one basically involves an R group that's attached to that OH, then OR group on the left, OR group on the right, and then this base, like another R group underneath that.
Mm-hmm.
So that's basically going to be a ketal, because you don't have it attached to like an OH, for instance. You just have it attached to like OR groups.
Okay.
So so let me see like the explanation. So let's see. Sucrose does not possess a hemiacetal functional group, so it won't be oxidized. Saccharides undergo, okay, blah blah blah. Reducing sugars, blah blah blah. Yeah, it doesn't give you. That's a crappy
Yeah,
explanation.
they're just most of the time they're like the answer is. Because
Yeah,
we
they're
said-
tautological. It's like the answer is A because it's A.
There was an answer in one of the questions when I was reviewing it. It said the answer is obviously, like they used that word. I'm like, really, guys?
They're like condescending as hell. Yeah, I can send you some material on that because that
Okay.
kind of gets pretty annoying.
Yeah. They do seem to like to test this kind of stuff a little bit. I mean, I'm decent with carbohydrate,
Yeah.
structures, but that question was a little bit. I mean, I still get it right, but like.
Oh,
I mean,
yeah.
I mean, these two
From
are very
seeing
close
what-
in structures.
Yeah,
Like,
yeah.
a lot of times, if you pick something, like you can kind of look at the orgo and not know what's going on and still get it. But
Mm-hmm.
it's Michaelis-Menten. I'm pretty good with Michaelis-Menten stuff. So
Mhm.
what did I get wrong? Let's see. Yeah, I did get on this passage, except this one question. What did I miss here? Oh, I made a really big mistake on oxidation versus reduction, and I think I made this mistake on 2 questions and I got it wrong because I
Mhm.
flipped what they meant.
Oh, yeah.
Because I was thinking of it from the biology standpoint, and I think that's what messed me up. Let me see, what question was this?
Yeah, if something gets oxidized, it's a reducing agent, right?
Yeah, and I didn't even know in my head reduction is loss of electrons, right?
Gain?
I mean, reduction's gain of, sorry.
Yeah,
Reduction's gain of
GER.
electrons. And I said, let me see what this said real quick.
Yeah, but the main thing is that if something gets oxidized, it works as a reducing agent. Because it reduces the other thing.
Yeah, I should have just looked at this. NADPH is oxidized NADP plus, right? No, wait, that's why I got it wrong.
So it gets oxidized, but that means that it reduces other things.
It's the reducing. Wait, so NADPH is oxidized, but
Mhm.
that means it's the reducing agent.
Yep.
NAD plus, if it went this way,
Yeah.
it's being reduced. So that's the reducing agent.
If it's being reduced, it's going to be the oxidizing
It's
agent.
oxidizing agent. Okay,
Yeah.
I got that backwards.
Mm-hmm. Yeah, redox always needs both parts. There needs to be something that gets oxidized, something that gets reduced. So the oxidizing agent oxidizes something else, and that something else reduces it.
But I also think the reason when I read it,
Mm-hmm.
I wasn't using that even. I was saying, I
Mhm.
think I was like, oh, NADPH here is losing a proton. So it's,
Oh yeah, so that's something to know for like this. Also with NADH, it's not a proton; it's a hydride. So hydride is a hydrogen with 2 electrons, so it has a negative charge.
okay.
So that's why when you have like NAD plus, getting reduced, it turns into NADH plus H plus.
Gotcha. Okay.
So that hydride thing is very, like, remember that, because it's not H plus. Because
Okay.
if it goes from NADP plus, right, to just NADH with something that's neutral, that means that it has to gain a negative charge, right?
Yeah.
Yeah. But that's tricky for a lot of people because they usually think of H as H plus, but it's a hydride in this case.
Okay.
Yeah.
Oh, this question threw me off pretty bad. This was a physics question.
Oh, yeah. So let's see. End of reaction 1. The level of the aqueous solution was 26 centimeters higher inside the burette than outside. Compared to ambient temperature, the pressure of the gas inside the burette would be... Okay, so we have lower, same, and then 2 that are like talking about how much greater it'll be.
I just thought that it would be. I'm trying to remember. Make sure I understand why. Hold on.
Mm-hmm.
There was a reason why I picked Sam. Hold on, let me think first. Hold on. There was something in the passage that maybe I'm trying to use passage too much. There was something I saw and it threw me off.
Yeah.
What was this? 23. Passage said pressure inside the lungs would become equal to the pressure of the atmosphere.
I inferred that meant pressure of gas in the burette was the same. I should have thought pressure is inversely proportional to volume.
Yeah, so I was lost and I was like, oh, well, the passage says this. And it was like compared to the ambient pressure.
Mm-hmm.
Yeah. So I guess it got me on what I did wrong here because I guess I get and understand the concept that well or something.
Okay,
But
so it seems like they
it
do
was
some...
up here. It was somewhere when movement particles along required lung volumes increase, pressure decrease, this is the PV is nRT, right? And the movement of gas particles into the expanded lung volume allows the pressure of the lung become equal to the pressure of the atmosphere.
Uh-huh. Okay, now this is talking about magnesium. In acid, it produces hydrogen gas. So it basically creates gas. So let's see. They made a vacuum in the burette, and then it was filled with water from the beaker. Air was then allowed through the tip of the burette until the water level decreased. Then they added the acid, and then the magnesium ribbon reacted, meaning that it made the hydrogen gas, and it created a difference in the water level.
Should I have thought decreased volume is increased pressure?
Wait, what's up?
Should I have thought by reading this here though? Because I'm trying to understand how the experience said water level was red. Wasn't the water the volume? Because it says something about decreasing. Hold on, it was up here. Never mind. I thought it said something about the volume decreasing. Never mind.
Well,
That's
they
good.
said the difference between the two readings was the volume of the hydrogen gas produced.
That'll just be the moles of gas, though, right?
Wait, what?
That'll just be the moles of gas produced, is that what they're saying? The volume, or just I'm getting lost. Hold on.
Yeah.
So, I kind of understand the relationship of the PVs and RT formulas. Isn't that what we're testing? Is that what they're testing here?
Well,
They're testing.
that's that's part of it, but it seems like what they're doing is it's like this beaker of water. They put this upside down burette in there, right? And they basically create a vacuum in it, so it's going to suck in some of that water. So water is going to be reaching to a certain point in there. And
So
when they do the chemical reaction by adding the acid to the magnesium, it's going to produce hydrogen gas, which is going to displace the water level. If the water level is at 25 mLs, and you do that reaction, it's going to create hydrogen gas, which is going to push the water, and it's going to give you a different water level, and that difference is going to be equal to the volume of the gas that's made.
okay,
So,
I think what I was trying to say now, since this thing, the what was it called?
The
The burette. Okay, since the volume of water, I guess, is rising in the burette, doesn't that mean that the pressure is decreasing, which is why A is the answer?
Well,
Because I think that's what they were sort of trying to say here.
the ideal
but-
gas law thing is different from, because I had a student that was confused about blood pressure, because she was using the ideal gas stuff, because that is very different. When the ideal gas law, where pressure and volume are inversely proportional.
Yeah.
That is talking about that's not talking about the actual the gas itself. For instance, what that is basically saying is that it's talking more about the container, if that makes sense, rather than the gas itself.
Okay.
So
yeah.
that's saying the PV equals nRT means that if you if you have a container of gas and you increase the volume, right? It means that the pressure is going to be lower because like the gas molecules have a lot more room to like do their thing. So it's talking more about the container. Now, if we're talking about the gas itself, right? Like, or like a liquid like blood, if you have an increase in the volume of the gas or an increase in the volume of like a liquid, it's going to press against the container, creating more pressure. So that's an important distinction. Like when we're thinking about the ideal gas law, think about it's like the volume of a container. And in every other situation, like with blood and stuff, it's the volume of the gas or the liquid itself. And that if it's the volume of the gas itself, right, then an increase in the volume of the gas means that it's going to have more gas. So it's going to create more pressure. That's why like your blood pressure increases if you like drink a lot of water and you have higher blood volume. Like if you're like, you know, like God forbid get like shot or something and you're losing blood, what happens to your blood pressure? Or think about Lance Armstrong, right? When he did the thing where he put in his own blood with more red blood cells.
Yeah.
Do you think, what would that do to his blood pressure? Imagine your blood, you just have more blood in you. It's going to be too much. It's going to raise your blood pressure. All right, okay. But for this question,
I'll be honest, pressure is not my favorite topic of physics. Like, yeah, I've not actually studied this topic as much as I should. I like stop at PPs and RT.
Yeah. It's going to be very
the fluid stuff. I've
opposite
not
with
covered very
fluids.
much,
Yeah.
I'm being honest. I just have a hard time understanding it. Okay.
Oh yeah, so for this one, let's see. Pressure builds on the inside by raising the liquid level. Yeah, when the sum of the inside air pressure plus the liquid pressure equals the outside air pressure, the liquid level stops rising. Okay, so they're saying that at the end of reaction 1, the level of the aqueous solution was 26 centimeters higher. So that basically means that that's like the amount of like the gas that was made. Now let's see, compared to the ambient pressure, the pressure of the gas inside the burette would be lower, the same, or greater. Okay, so okay. It's like, I don't know if we worked on a question like this, or maybe that was with another student, but there was like a question. All right, forget that question then. But basically, the greater the ambient pressure, which is the atmospheric pressure, if you go back to that picture. So, okay. If the pressure of the atmosphere pushes down on the surface of the water in that beaker.
Okay.
And as that presses down on it, oh wait, so this burette is air was then allowed in through the tip of the burette until the water level. Hold on. So okay, wait. This is a little different because they're separating this. They're not letting water enter in. Wait. Can I see just scroll up a little bit more? Okay. Open end of a burette. It was inverted into the beaker. Okay. Vacuum was used to suck out of the tip of the burette, filling it with water from the beaker. Okay, so it is kind of connected. All right. Air was then allowed in through the tip of the burette until the water level decreased. Okay, so basically this is what they did. So they put that burette in there, right? And they created a vacuum, which means that the inside of the burette has nothing in it. and aka the pressure inside of the burette, 0. So naturally, the water is going to be sucked inside of the burette. It's going to be sucked inside, and it's going to go up, like, basically to some high level. And then they let air into the burette. So in that tip of the burette, that was a vacuum before. Now they let air inside, which pushes down on it. So it lowers it, and it lowers it down to the 50 ml mark, which is the highest mark in the burette. Okay. Then they did the thing where they created hydrogen gas, and then they read the water level. And then they said the difference between the two. Okay, so at the end of it, the level of the aqueous solution was 26 centimeters higher inside the burette than outside. So that basically means that that magnesium thing inside, it makes the hydrogen gas, which pushes, like, you know, which has a volume of its own. It pushes the water to a higher level, which is whatever, 26 centimeters, I guess. So it's higher, 26 centimeters higher inside than outside. Now, compared to the ambient pressure, the pressure of the gas inside the burette would be what? I mean, okay, so like if it's creating gas which pushes this thing upwards, it's going to be higher. Okay, let me try to think about this because this is kind of weird. I don't know if I like completely get the. Let me see what you said. I thought pressure is inversely proportional to volume.
Yeah, I looked this up on Reddit, and that's how they were explaining it, but I don't know, some weird stuff on there that's not necessarily right. But I thought that they were talking about the PV as NRT, because the way they explained it down here was like...
Let's see. Because the level of the liquid inside is higher than outside, which results from the fact that the air pressure outside is higher than the pressure inside. Pressure builds on the inside by raising the liquid level. When the sum of the inside air pressure plus liquid pressure equals the outside air pressure, the liquid level stops rising. Okay, so I guess like there. Okay, so this is like that other question that I was working on. So yeah, okay, since basically it's the same kind of thing that I was thinking of before, I should have just explained it this way. The pressure is pushing down on the water surface of that beaker.
We're talking here.
Yeah, it pushes down on that, which makes the water inside the burette rise, basically.
I understand that. I can see that.
Yeah.
Cool.
Since it's, above, it's higher inside than outside, it means that the pressure, the atmospheric pressure or whatever is going to be greater than whatever it is on the inside. There's another question that's like this that I'll send you.
You're losing me now. Okay, so we have a pressure here, and that's causing the volume inside the container, the whatever you call it, this to rise. The burette is causing the volume to rise. Okay.
Mm-hmm.
I got that. Hold on. We're saying the pressure outside is more than inside?
Yeah, because it's pushing down on the water, which causes the thing inside the burette to go up.
That's why this is going up. All right, I'm following that. So we have higher pressure outside, basically the burette, pushing down on the fluid, the volume in the beaker, which causes it to rise. I get that. So since pressure is it, but still I'm seeing it in terms of, since the volume of what's in the container is going up, that means that the pressure of the gas would be going down. I'm still seeing it as an inverse relationship though.
Wait, you're saying since the volume, you're creating a greater volume on the inside?
Yeah, the volume is, the fluid's rising inside, right?
Mm-hmm.
So since that's going up, that would mean that the pressure of the gas is going down. Because that's right. Or I was saying the pressure of the gas. Yeah, the pressure of the gas, because volume's increasing, pressure is decreasing.
Well,
I guess because somebody on Reddit said that's why that was the answer, but like, they're not this. They're going a little more in depth here.
yeah,
But I mean,
because
I guess like if volume's increasing, the pressure would have to be, if the gas would have to decrease, wouldn't it? Or no?
so that's again just like for like an ideal gas, and we're kind of like thinking in terms of like the liquid and stuff like that. But like here, maybe this will help. I'm gonna share my screen. All right, you can see this.
Yep.
All right, so this is like the question I was thinking of. This
Okay.
is basically a tall tube is evacuated, right? AKA a vacuum, right? So they get rid of like the air and stuff inside.
Mm-hmm.
And its stopcock is closed, so they just close this for now.
Mm-hmm.
The open end of the tube is immersed into a container of water, like this, which is open to the atmosphere. So atmospheric pressure, right, is pushing down against the water. Okay?
Yeah.
And that means that since there's like another way for it to go, atmospheric pressure, as it pushes down on the water, it pushes it into this tube. Like, so okay. Like it's pushing down here, and so fluids don't work like gases, they're not compressible. So if you press down against like a fluid like water, it's not going to like compress. Like a gas can compress, right?
Mm-hmm.
A liquid can't. So if you're pushing down against it, and the only way for it to go is up into this, like, imagine like it's a tube, but in the question you had, it was a burette. The greater the pressure on the in the atmosphere, the more this water is going to rise inside of the tube.
Mm-hmm.
So like imagine this stopcock was opened like this. It's going to cause this water to rise on the inside. And it'll rise to like a certain height. It'll rise to like a height where basically this is like the vector for the weight of the water, and this is like the vector for the atmospheric, like the force caused by the atmosphere, and those two will basically be equal. So I wrote here at first, yeah. So basically, it's this type of principle here. So in order for, like, just because inside of the tube the water level is higher than it is like down here in the outside, like in the beaker, that means that the atmospheric pressure is greater than the pressure inside, because the atmospheric pressure is what causes that water to enter that tube in the first place.
Yeah, I definitely follow that.
Yeah. So this is kind of like the same. It's a little weird with the chemical reaction involving the hydrogen gas and stuff, but it's the same question, but this is just a burette in the question that you have. And overall, what happens is, like, the water level increases. And it would only increase if the pressure inside is less than the pressure outside. If the pressure inside is greater than the pressure outside, the water would push down, right? Causing the water level on the outside to go up.
That's right. So that makes a lot of sense.
Yeah.
Okay.
But since it's greater on the inside, it means that the atmospheric pressure on the outside is greater, causing it to go in that direction.
Okay. Well, that made a lot more sense actually then. But
Mhm.
yeah, that's helpful. So I mean, like some of these questions I didn't have a hard time with, but
Yeah, it seems like you're doing pretty well. Good.
yeah, some of these I took way too long, but I mean, I did do them. Yeah, I don't understand. I didn't understand the Doppler effect that well. Like sometimes I get it, and then sometimes I don't. Um,
Mm-hmm.
what this was Doppler effects. I did not like get this.
Okay.
Basically, yeah, this is the same type of thing I got wrong before with basically like units, but this is just talking about the Doppler effect.
Yeah. Yeah, so the Doppler effect is basically there's a moving object that emits some type of wave, and there's a stationary observer that isn't moving, and as that moving source of like a wave or whatever like moves towards it, the frequency is going to be higher like for the stationary observer than what the frequency is like naturally from that moving thing, and as it moves away from it, the frequency is going to be lower than what it is normally. So that's why like like an ambulance, like as it like the ambulance, if an ambulance, let's say you're like standing in the middle of a street or something, and an ambulance right comes in, you're the stationary observer, you're not moving, ambulance is, so it's the moving thing that is giving off like sound like a siren, and as it gets closer to you, the frequency of the sound goes up. So in sound, that means its pitch is going to go up. It's going to go like until it goes exactly where you are, which is where it should be. Like it'll be the exact same frequency. And then as it moves away from you, it's going to be a lower frequency, so its pitch is going to go down. It's going to get deeper. So okay, so let's see. It requires what minimal information? Speed of sound in the moving object. Speed of sound.
For all of them, so.
Wait, what's that?
I said that was for all of them, so I now at least knew all of them.
Oh yeah. So yeah, you can cancel that out.
Yeah.
Speeds of sound and of the moving object, and
so apparently we don't need the moving objects, and I didn't know that.
You mean the speed of the moving object?
Yeah, it says we don't need the moving object.
Yeah, they're saying the
So
minimal...
I guess that must be an always situation. So it's stationary.
Oh yeah, because it just says minimal information. So they're asking what. Okay, so in order for you to observe a Doppler effect, what's the minimum amount of information you need to know? So like in the example I gave, you can tell that when an ambulance is driving and whatever, you can observe that Doppler effect, right? You don't need to know this speed of the ambulance to observe that, right?
Yeah.
But
I think when I did this one, like I knew that this wasn't the right information because I knew how to do it with the frequencies. Mm-hmm. So,
yeah. So basically, C and D.
I'm not sure about wavelengths.
Well,
so
if you know
I think I rolled this out because I didn't remember anything in the formula specifically addressing wavelengths. Like I'm not trying like just to memorize the formulas, but I didn't think that mattered.
Yeah. So C and D. So like if you have the speed and frequency, you're going to be able to get the wavelength because frequency times wavelength is equal to.
I wasn't even thinking about using those formulas, but yeah, that's true.
Yeah.
But I definitely got to B and C, and I didn't know.
Yeah.
I guess I didn't know why. I couldn't determine whether you needed the moving object or not. I mean, it just said motion of the piece. I didn't know whether you needed that.
Well, it says it's the speed of the moving object, by the way, right?
Speed, yeah.
So you don't necessarily need to know the speed of it because you can pretty much deduce that from the frequency, right? Like all you need to know is that the frequency that it emits and then the frequency that you observe, right? So like for an ambulance, right, it emits a certain frequency. As it moves towards you, the frequency that you observe is going to be higher. As it moves away from you, the frequency that you observe is going to be lower. And as it's just passing you, like right in front of you, the observed frequency and the emitted frequency are going to be the same. So this is just basically asking what is the least, like the least amount of information you need to know in order for you to observe the Doppler effect.
Okay.
And just think of like that ambulance example. Because like the frequency you can observe from the pitch, and yeah.
Yeah. Okay. Yeah, I was 50-50 on this, and I don't understand why C is the answer. Like, I just don't get this. So, like, I guess, which of the following statements explains why the boiling point of HF is abnormally high when compared to the boiling
so
point
when you're dealing with boiling points, like, think about, so like when something boils, right? It, you're adding heat, enough heat to overcome and break the intermolecular bonds between the molecules. And what's the strongest type of intermolecular bond?
covalent.
That's an intramolecular bond, which is within the molecule. But
Outside, was that like the Lewis, or not? Sorry, the H, whatever you call it, the I can't think what it's called. London dispersion forces.
So that's a type of intermolecular bond.
Okay, never mind.
No, that's a type. Yeah.
Okay, so yeah, so London
what's the
dispersion
strongest
forces, and then, or off the top of my head,
What are the types of bonds between the bases in DNA?
I don't know, I'm losing myself today. You mean like H bonds between?
Yeah, hydrogen bonds.
I didn't know if you were talking about, like, I was thinking of something else. Yeah, the H bonds between, like, yeah.
Mm-hmm. Yeah, so hydrogen bonds are the strongest type of intermolecular bond. And they're going to, so remember this, I'll write it in the chat, F-O-N, FON. These are the elements that can participate in hydrogen bonding. Of course, H as well. So like an OH group will make a hydrogen bond with like an F or you know, an N or something like that.
Oh, that also happens too with like the base pairing, doesn't it? Like with the yeah, so
Between,
that's why
like, an NH group.
that's why like
Yep.
adding the diamine pair up is because like the NO or whatever, right?
Yep.
Yeah. I knew that what it looked like, but I wasn't sure. I think when I read this question, I rolled these out, but like HF is affected by H bonding interactions to a much greater degree than group 7A. I just didn't understand why HF was more than the other ones. I thought it had more to do with the polarity was different going down the periodic table compared to the other halogens. So like I knew fluorine was at the top.
So that should make it more
didn't know
polar.
how I knew for sure. I guess I didn't know for sure how I knew that there was more H bonding going on there. So that's why I went with the polarity. I was like, oh, well, I know there's going to be a difference in polarity. I thought it would be more significant.
Well, an
going
HF
down.
bond should be more polar, though, right? Because electronegativity, like, goes up if you go, like, you know, to the right and up in the periodic table.
Oh, shoot, you're right. I was never paying attention to that. I was just thinking this didn't sound right at first. I was like, oh yeah, polarity difference.
Yeah,
So-
yeah.
So I guess I couldn't verify like to myself.
Mhm.
I should have seen that much less, not greater. I was paying attention, but like
Mhm.
that's how I would have gotten it. But like I didn't know for sure that it was more affected by H bonding. Like how I would know that.
Yeah, so remember FON,
Okay.
all right? I put that in the chat.
So F has more H bond. Is affecting more of
So
H bonding.
H bonds are only going to work with, like, obviously hydrogen and FON. H bonding
Okay.
doesn't work for anything else. It only works
Okay.
for fluorine, oxygen, nitrogen.
Okay.
Okay? And when you think of boiling point and stuff, think of intermolecular bonds, especially hydrogen bonds.
Okay.
That's why water has such a, you know, high boiling point compared to other things that are like that.
Okay. This is another one of those like not knowing what things mean.
Oh yeah. Oh, okay. So principal quantum number. Yeah. So this is like n. What is there like?
Yeah, I was like, it wasn't like the MS2 and all that stuff.
ML, MS. So like n is a principal quantum number, so that just basically gives you like basically its size. L gives you its shape, I believe. ML, yeah. So yeah, it's the size basically. Yeah, okay, so the shape should be the L part.
Okay.
Yeah. Number of valence electrons is going to be, I guess, like the ML thing. But
Oh, I guess I was confused because don't they show like in the chart like n equals some number?
well, in the periodic table, like you can know what n is by looking at what row it is. Like the first row is 1, second row is 2, third row is 3.
Oh, okay.
You know, and like
Yeah.
1s, like 1s2, 2s2, 2p.
Yeah, I was
6.
thinking of electrons though. Oh, yeah, I don't. Okay.
Well, yeah. But it's like the size of the electron cloud.
Not the number of the valence electrons. Okay.
No, that'll be like basically like I think like the ML number.
Yeah, I didn't have that conceptually like memorized or understood that well because they don't really ask about it. But
Yeah, that's true.
I never even learned it in chemistry. I mean, like we kind of over.
Yeah, but it's like so early in chemistry that most of the time
My
we're just,
professor was like,
forget
"This
it.
is pointless. We're not learning this."
Yeah.
Why
Yeah,
do they test a lot of pointless concepts?
It's the
Like
size,
whatever. Okay, so I'll just remember. So L is shape, N is the radial size of electron clouds. I knew this was stupid. That wasn't the answer, but I guess I went. Yeah. Okay.
Yeah, that's like the ML, I think. ML quantum number. Yeah. Okay.
I think 30 I wrote don't get this. I was between I actually eliminated B, and that was the correct answer. Well, I'm trying to think why. Let me go up and try to I think it had to do with this relationship that I misunderstood and got backwards when I was trying to like read the information on the graph. Let's see what CPFX was again.
I think we could get this just from the. Let's see. Oh yeah, just from the table. Like the above that, the first two tables.
This or this one.
Like the first two, yeah. Because you see how there's a Ka to K naught ratio. So
Yeah, I had a hard time understanding exactly what that meant, and I was getting really thrown off here. But
yeah, so basically they give you Ka, right? And then they give you the Ka to K naught ratio, and K naught represents the affinity constant of CPFX in the presence of BSA only. So let's see. For warfarin, there's a smaller number compared to ibuprofen. So, like, basically, like, K naught is going to, like, increase, like, you know, because it's a denominator. So, like, as K naught increases, divided by K naught will decrease. So anyway, table 1 just gives us the values when it's just in BSA. Now, table 2 gives us the values of when it's with BSA, but also in a metal ion. Okay? So, if we look at these values, and then they say for table 2, K naught is the binding constant of it in the absence of a metal ion, right? So, it seems like, so that, you know, they're basically just showing like how it relates to the presence of metal ions, right?
yeah.
So okay. So question: metal ions are expected to, so like here, go up a little bit more. So analysis of the data, let's see, warfarin and ibuprofen, okay, effective metal, okay, 2 and 3.
Wait, so is this
Yep.
this is I thought this was presence. Is this presence or absent?
So
I think that's where I got confused.
So Ka is presence, K naught is absence, right?
Okay, so I might have misread that.
So
So I
if-
was saying like,
So if it binds, if K naught, so if it binds better, sorry. So so Ka here is when it's in the presence of the metal ion, and K naught is when it's without the metal ion. So if it binds better when it's in the presence of a metal ion, Ka will be greater than K naught.
okay, so am I supposed to think of Ka as like the binding affinity?
Yeah, when it's of BS of CPFX and whatever it binds to, right? Like in the
So
presence
this
of,
is the absence of the metal ion.
so
This isn't the presence.
so that's the presence, and then on the right it's the presence divided by the absence. So
But in
what to
the
do with
presence,
that?
it's greater binding, right?
So if it's Ka is when it's present, metal ion is present. K naught is when it's absent. So if it binds better, when it's absent, right? That K naught is going to be a larger number.
Closer to 1, yeah.
So if it's a larger number in the denominator, you're going to get something smaller than 1, right? So like, just think of it like, so Ka, right, is in the presence of a metal ion, and K naught is in an absence of a metal ion. Now, when they do Ka divided by K naught, since all of these values are less than 1, it means that K naught is greater than Ka, right?
Yeah, this is where math sucks for me. So
Yeah,
that's
so
I had a hard time with this. So because I understood, and I hardly was even looking. I was really confused by this. Like,
yeah,
because they give you what K naught was.
so they don't give you K naught, but they give you Ka to K naught ratio. But basically, all you need to think about is this. Okay, K naught is the denominator, right?
Mm-hmm.
So, okay, let's say K naught is less than Ka. Then when you divide Ka by K naught, you're dividing a number by something that's smaller. So you should get a bigger number, right?
Okay.
Like if I write Ka over K naught, and then let's say Ka is equal to 2 and K naught is equal to 1. Then Ka over K naught is going to be 2 divided by 1, which is 2, right? Right?
Yeah.
Okay. So basically a number greater than 1. What about when Ka is equal to K naught? What would Ka over K naught be then?
It's not. Isn't it going to equal Ka or?
So if Ka is equal to K naught, so let's say Ka is equal to 2, K naught is also equal to 2. 2 over
Okay.
2 is equal to 1, right?
Okay.
Okay, so if K naught is less than Ka, when you divide Ka by K naught, you're going to get something bigger than 1. And when Ka and K naught are equal, you're just going to get 1. But let's try when Ka is less than K naught. So let's say Ka is equal to 1, K naught is equal to 2. Then Ka divided by K naught is going to be 1 over 2, which is 0.5, which is less than 1, right?
Yeah.
So basically the idea here is just like since all these values for Ka over K naught, are they less than 1, greater than 1, or equal to 1?
They're greater than 1?
Wait, are you sure? 0.87?
Okay. Wait, the Ka is greater than 1. The Ka is
Yeah.
greater than.
But we don't care about the exact values of Ka. All we care about is this ratio. So Ka over K naught. Look at all those values. Tell me, are they...
They're all less than 1, though.
They're all less than 1, right? That means that K naught is greater than Ka. In order for the number to be less than 1, the denominator has to be greater than the numerator.
Okay.
So the data shows us that this ratio is less than 1. This means that K naught, which is the binding constant in the absence of a metal ion, is greater than Ka. So when there's no metal ion, its binding constant is greater than when there is a metal ion, right?
Hold on. Let me think for a second. Okay, so K naught, this is presence of binding metal ion. This is with, wait. Okay, yeah, so this is presence, Ka, this is presence, this is absence.
Well, that's the ratio. They're gonna be a little bit so yeah, Ka is the presence. Ka over K naught is just the ratio of the present to the non-present. They're not gonna be they're not gonna make it easy for you by making it K naught only in that column. But you don't have to worry about the Ka values. You just need to know if it's equal to 1, less than 1, or greater than 1.
Okay. Well, I know, I see there's less than 1.
So if it's less than 1, that means, see how it says Ka divided by K0?
Mm-hmm.
By the way, when I say K naught, you know I mean K0, right?
Yeah.
Okay, so it's Ka divided by K naught. So if it's less than 1, it means that K naught is greater than Ka, right?
Okay.
Whenever a denominator is greater than its numerator, the overall value is going to be less than 1.
Okay.
Right? And you can plug in numbers if you want. Give me a number for a numerator, any number.
5.
And pick a number that is greater than that.
8.
Okay, so then 5 divided by 8, that's going to be less than 1.
Yep.
Okay. Now, if they're equal, 5 divided by 5, it'll just be equal to 1. And if Ka is greater, it'll be 8 divided by 5, which is greater than 1. So,
Okay, so if the denominator is greater, it's less than 1. I
Yep.
can kind of see that mathematically in my head now. Okay.
Yep.
I was just really overwhelmed.
Yeah.
Because I was trying to relate this and KD and all right. I have a hard time sometimes with these kind of relationships. I get it now that we're talking through it, but
Yeah, because look, they could have made it straightforward by having one column be Ka and the other column be K naught, but they're not going to make it that straightforward. So this is where, you know how I always talk about ratios, thinking of things in ratios? Mm-hmm. Knowledge of ratios will help, because then it doesn't even matter what Ka is or K naught is, because you can basically just all you need to know is it less than 1, equal to 1, or greater than 1? So since all these values are less than 1, it means K naught is greater than Ka. So, and K naught is the binding constant in the absence of a metal ion. So metal ions make it worse, make it bind less, because it binds a lot better when there isn't a metal ion.
Okay. So just go through this one more time.
Mm-hmm.
K naught is the binding constant of this without the absence of a metal ion, but we don't know what the value for Ko is. We know what Ka is, so I'm supposed to just look at this ratio and understand that since these values are less than 1,
Yep.
that means the denominator's bigger
Yep.
for Ko.
Yep.
So K. All right, so that, all right, whoa, hold on. So Ko is, and I'm getting lost now. I was talking through and I'm getting lost. Hold on. Okay, that's in the absence.
Yep.
I'm getting lost again. Hold on.
So like K naught is bigger, right?
Yeah. Okay. Yeah. So the denominator. So it's, all right. So since that means the denominator for K naught is larger.
Yeah, the denominator is K naught. Yeah.
Which means what again in terms of the CPFX bound to BSA? I'm getting like lost now again.
Oh yeah. So you know, so we know that K naught is bigger, right?
Yes.
Okay. So, and then they say K naught is the binding constant of that crap without a metal ion present. So its binding constant is greater when there isn't a metal ion there. So, in other words,
We're saying so because, hold on. So because the K, all right. So here we go to here. Because K naught is a larger value than the numerator Ka.
correct?
In the absence of the metal ion, that means more of CPFX binds to BSA.
So well, K naught is when it's in the absence, Ka is when it's in the presence. And since K naught is greater, it binds better in the absence.
It's kind of hard to keep track of.
Yeah. Just
like,
think of it
like
like I would just write maybe something like, so I would write like this. I'd put it in the chat. Ka is equal to binding with metal ion. K naught is equal to binding without metal ion. And K naught is greater than Ka. So binding is better without metal ion.
So if K, so if
Yep.
So if Ka over K, if Ka over K naught was 1,
then it's going to be equal.
equal.
It'll work
So
as
that-
well with metal as it will without metal.
And it's like I understand the like what the relationship in terms of like the binding affinity, all that. It was just hard for me to get that part of them.
Yeah. They you know they want you to be very like math, like being able to like read the table and see, because they don't want you to, like, a lot of people will just look at the 2.03 number and then the 1.538 number, but you know, if you look at that ratio and you can just know if it's less than 1, equal to 1, greater than 1, you know, this kind of comes back to like that first question with the kidney stones.
Mm-hmm.
If it's equal to KSP, greater than KSP, less than KSP, right? So yeah, since these values are all less than 1, it means that the denominator is greater, which means K0 is greater, which means that binding works better without a metal ion.
Okay. I think I get it. I might have to like sit there one day.
Yeah.
I kind of get it. It's
Mhm.
just, yeah.
Yeah. So metal ions are expected to. So metal ions mess it up, right? It binds less when metal ions are there. So it's gonna decrease the amount of that thing bound to the other thing.
Yeah, I had the opposite answer. That's all right. The math sort of got me.
Yeah. It's weird.
Yeah, this was a hard passage. I think I got a lot of these wrong.
Mhm.
Like, this passage was rough for me. Like, it ruined the whole test. Oh yeah, I got this question wrong. Something I didn't know. I went with glycerol, I think, which naturally occurring biological molecule would be most likely to bind in the same site as ibuprofen. I'm like, oh, this is gonna be an easy question. Let me go up here and figure out what the binding site is, and they don't tell you. Like, I went up here, binding sites that can accommodate structurally diverse ligands tend to be hydrophobic. I think that was a good clue. Electronegative.
Well, it says mainly hydrophobic with anionic or electronegative features. So part of it's going to be hydrophobic, and the other part's going to be like a negative charge or something that's electronegative. So, like, you know, glycerol is just going to be like hydrophilic.
Yeah, because it's polar because of the OH bonds, I guess.
And then
I knew the A and B were dumb. I knew palmitoleic acid was a fatty acid, so I guess I should have thought hydrophobic.
Yeah, because the
tail had
Yeah, because a fatty acid is just like a glycerol with like those the fatty like a fat is just like glycerol with the 3 fatty acids attached to it. And so palmitoleic acid, blah blah blah, that's basically, it has the acid part, which means the acid part loses a hydrogen, so it becomes negatively charged, so that's an anionic feature, right?
Yeah, and going through it, I didn't highlight that. Mm-hmm. So
Yeah. When you were saying it, I heard you say hydrophobic, and then I right away was like, it says mainly.
I was getting frustrated because I was like trying to look like for something. Actually, like they're like, oh, ibuprofen. I'm like, wait.
Yeah.
And this really didn't help you because all you see is the COO.
Yeah, because it just shows
you see that's electronegative, but like you didn't see anything else to suggest.
Yeah.
You didn't see anything that.
Yeah. Mm-hmm. Like I would highlight like.
A lot of the time you hunt for things, they'll show you the molecule or they'll say something about the binding site, like, oh, this is, whatever.
Mm-hmm.
Chymotrypsin, they'll talk about stuff. And this was tough about this sample test. I feel like it's hard because harder than some of the other questions I've seen from them because, like, I feel like a lot of these questions don't give you much to work with in the passage, or I was using things in the passage and I was still wrong.
Yeah, so for that one, like, I would just highlight, because you highlighted hydrophobic, but also the anionic part.
I think, too, I was like, right away, I should have read the whole sentence. Maybe I'm like, here we go. That's the clue. Let's go. And,
yeah. But like, even if you looked at that part, then glycerol wouldn't work because that's hydrophilic, right?
Yeah, but I was thinking at the time.
Yeah.
I was thinking it was
like a triglycerol.
Yeah, I was thinking, this is
because that would be.
I was thinking it was hydrophobic at the time, but I wasn't thinking it was glycerol by itself. I was thinking it attached to things, and then I should have. I see that. I reason myself out of this for the reason I picked glycerol.
Yeah.
If they had said like tag, and
triglycerol.
Triglycerol, that would have made more sense for me, right? But I mean, it's the same thing basically. Like it has the polar.
Yeah, like it has the part that's an anionic, the acid part, and then like the long tail is the hydrophobic part.
Yeah, I was 50-50 and I picked the wrong one here. Based on the data in table 1, the binding site of CPFX on BSA was determined to be what?
Let's see.
I mean, this may have to do with the math again, me getting it wrong, like getting the relationship backwards or something.
Wait, let me see above that where it talks about site 1 and stuff. Okay, let's okay. CPFX. Okay, so all right, so warfarin binds to site 1 or warfarin has whatever CPFX bind to site 1 and ibuprofen has CPFX bind to site 2. And
Yeah, see, the way they worded that really confused me.
oh,
Like,
it says respectively. That's what gives it away.
so site 1, site 2.
Yeah.
I figured that out when I read it, but I was
Mhm.
kind of pissed off because I felt like it didn't describe much. So then I looked at this. So I'm like, okay, site 1 and site 2. So I got to that.
Mm-hmm. Okay, and all right. It seems like K naught in this case is the affinity constant in the presence of BSA. Wait, BSA only as opposed to what? Presence of warfarin and ibuprofen in the presence of BSA. Wait, BSA alone. Oh, and then BSA with warfarin. Okay, got it. So here K naught is just with BSA, and KA is with warfarin, or for the second row, ibuprofen. So let's see. So K naught. Tell me for warfarin or ibuprofen is which one is K naught greater?
It's greater for ibuprofen because the denominator, right?
Well, check it out. So if the denominator, they're both involve a denominator that's bigger than the numerator,
Okay.
right? But which denominator is bigger?
I think isn't it the 0.4 because it's farther away from 1?
Yeah, it's smaller, right?
Yeah.
So that basically means that warfarin, which is on site 1, like the site 1 thing is not that good at maybe that's not like a good site for it to bind to. Maybe site 2 is better because ibuprofen is for site 2 and that gives us a larger number. So this one, looking at the KA can be helpful here, because KA is KA, right? That's for in the presence of the warfarin or in the presence of the ibuprofen. The KA is greater for ibuprofen, right?
I knew this was gonna be something confusing. I basically looked at KA, but I was trying to think binding, I know what the KD is for KD, the closer it is or greater, isn't that better?
Yeah, then PK is going to be the inverse, but yeah.
Yeah. So maybe.
Yeah, so the Ka is higher for ibuprofen, right?
Yeah.
So it binds better in the presence of ibuprofen than warfarin, right?
But it's
Yeah. So
but it says primary site 1 though, and warfarin's primary site 1, right?
Oh shit! All right.
That's why yeah. That's why I got it wrong.
All right. Let me see. Go up again. Warfarin, yeah, okay, site 1. Okay, you're right. Okay, so that would mean that it binds less to site 1. What the hell?
See, but I think I was trying to some people were trying to relate K to KM. This was a confusing question. This whole passage really just threw me for a loop.
Okay. Oh, wait. Hold on. Okay, so they're trying to figure out where CPFX binds, right? Now, ibuprofen has site 2. So,
Yeah, that's why I was lost. I feel like this is a mistake on their end.
No. Hold on. Let me see. Warfarin competes for binding of. Damn it. Okay. I get it. Let's scroll up again.
All right.
So yeah, a little higher. I just need to see like what exactly is going on here. Like, yeah, all the way up.
Okay.
So blah blah blah. Okay, so binding. So albumin. Okay. Drug called CPFX and BSA. Okay. Now, binding constant of CPFX to BSA, and then. Okay. So let's see. So this is basically BSA binding to CPFX. All right. Okay. So let's see. Okay. So BSA is the thing that has site 1 and site 2. Okay. And let's see. So warfarin is what binds to site 2. I get it. So check this out. so okay. Warfarin binds to site 2, which leaves site 1 open to bind to CPFX. And ibuprofen binds to... Sorry, the other way around. Jesus. Okay. I think I understand this now. So imagine BSA as this thing with like kind of like an enzyme or whatever with two sites, site 1 and site 2.
An allosteric site?
Yeah. So okay. We're trying to... So BSA binds to CPFX as well as warfarin and ibuprofen. So when it binds... So warfarin binds to site 1. It occupies site 1. Ka is actually the binding constant of BSA to CPFX. In the presence of warfarin and stuff. It's not the binding of warfarin to BSA, which is what I thought initially.
That's why I got it wrong.
This is pretty... Yeah, so basically, when warfarin is involved, warfarin binds to site 1, and site 2 is open, and the binding of BSA to CPFX is lower, which means that it's not going to bind to site 2. Whereas ibuprofen binds to site 2, leaving site 1 open to let CPFX bind to it.
Yeah, this is really tripping me up. Like I have a hard time keeping track of all that. And it's so
Yeah, I understand it now from seeing that the binding constant is for CPFX and BSA.
Where's that at?
Oh, like above that?
This,
Yeah.
all the way. Okay, binding constant of CPFX to BSA was determined. In addition, known BSA binders, warfarin and ibuprofen were used to determine the specific binding site.
Yeah. So I at first thought Ka was the binding of warfarin to the thing, or ibuprofen to the thing. But it isn't. It's just the binding of BSA to CPFX.
Okay, well I didn't understand that. I thought this was binding to it and this was binding to it. So
Yeah,
they're
me too.
saying that where are they? How do you know that that's what's happening?
Because
Okay,
it tells you there,
see it.
and it does tell you in the beginning of table 1 and table 2, like CPFX, BSA binding. In
I
the
was looking at the
presence of-
table more than paying attention. So
me too. So now I understand. So basically, like warfarin binds to site 1, blocking it, and therefore the BSA CPFX binding constant is less. Because so warfarin means site 2 is open, but the number for Ka shows that BSA is not binding to CPFX. And
I'm getting like really visually lost here. Okay, are we talking are we saying just this warfarin for this table and just ibuprofen for this table?
Yeah, one sec. Let me get my... Here, I'm gonna draw this out for you.
Okay.
Okay, I'm gonna share a screen here.
I see it.
What? Why is it not letting me write? What is going on here? All right, let's see if I can just do it like this. Okay. Whoops. Whatever, I'll just use my mouse. Okay, this is, oops. So this is BSA. All right. Warfarin, ibuprofen. So, and then, okay. Is this freaking working? Alright, I don't know what's not working. I'm just going to continue using my mouse here. Okay, so all the warfarin binds to site 1. So here, then I'll draw CPFX. So when warfarin is involved, so like, you know, Ka is how well CPFX binds to BSA, right?
Mm-hmm.
So this is BSA, this is site 1, this is site 2. So okay, when warfarin is involved, warfarin's going to bind to site 1, and CPFX, site 1's going to be blocked. So it's going to have like a crappy time trying to get into site 1.
Oh,
So this number is
is
going to be lower, yeah. And then
I get that.
Mm-hmm. And ibuprofen binds to site 2, so CPFX can bind to site 1, so that number is going to be higher for ibuprofen compared to warfarin. Right?
Yeah.
So in the presence of warfarin, this constant, which is basically CPFX binding to BSA, is small compared to in the presence of ibuprofen. So, and warfarin binds to site 1, and ibuprofen binds to site 2. So when ibuprofen's involved, CPFX can successfully bind to BSA, which must mean that CPFX likes to bind at site 1.
Hard time visualizing.
Yeah.
I see it there. I'm having a hard time visualizing those spliffy numbers now. Hold on. So, okay, site 1, warfarin binding the Ka. I didn't remember that it's not warfarin that's binding.
Yeah.
BSA, it's the CPFX. Okay, is binding to warfarin. It's lower for site 1 than it is for site 2. So is it more open in site 1?
Wait, sorry, say that again? I was just restarting
Oh,
this.
I think I just answered it. Okay, I think I got it. That's why it's C. All right. So at site markers, warfarin and ibuprofen, you can see that CPFX binding is greater for ibuprofen. So the active site 2 is more blocked. But at active site 1 with warfarin, it's lesser, which means that site's more open for binding to occur for the CPFX on BSA. So that's why it sees primarily at site 1.
Mm-hmm.
Because the site's more open. It says they're 50%. I was thinking of it the other way, that like, yeah.
Yeah, me too.
I I was on track and I had it backwards. That was a really difficult. I mean, it wasn't that it was so hard. It's just that.
Yeah,
maybe
I
made
had the
the
wrong
assumption. It's just
idea.
sometimes the AMC doesn't explicitly state things in a way that makes sense. And
Yeah.
it's just kind of backwards.
Mm-hmm.
Yeah, I hate them a lot. All right. Yeah, and again, I usually don't get amino acids wrong, and I got this one wrong.
Yeah,
I think I just made a mistake. So I wanted
share your
to.
screen again.
Oh yeah, that's right. Sorry.
Mhm.
Yeah, I got this amino acid question wrong, and I rarely get those wrong. It said site 1 and 2 are most likely aligned with what? And I think I couldn't figure it out if it was like what the
Okay, so they said that
hydrophobic.
it binds anionic stuff, right?
Yeah.
So I'm gonna guess the sites are gonna have positively charged. Wait. Okay. Yeah. Positively charged ones, right?
Yeah, I said negatively charged. I think is what I did.
Mm-hmm.
I guess I didn't.
Like the ligands are hydrophobic and anionic. So
I was thinking it told me basically negatively charged, so it would be the opposite. The positive would want to bind to it.
yeah.
I was saying they were negative.
Yeah.
Like I'm trying to
that's
say
the
what
ligand.
they were. Like that could be what amino acid they were, but it would be the opposite of what binds to.
Mm-hmm.
Yeah, I had it backwards. Okay. I hate that I miss stupid stuff like that. Like.
Yeah, but I think that's like relatively common for these problems because they're pretty. That was pretty tricky.
Like these kind of questions down here, I'm getting a lot more of these right.
Oh yeah, this is like like proportionality, like basically.
Yeah. Do we have about 30 more minutes?
Yep.
All right, cool. So these were math that let me make sure. I knew what this formula was. I think I knew how to, I just need to go through the math on my own, all that. I knew the formula, I just plugged stuff in wrong. Let me see, 37. I was gonna redo all the math ones that I got wrong. At 38, I put no clue, so let's go through that. Yeah, this is a notorious, like I've looked this one up before and I've never gotten it right on my own. I don't know if this is like one of those things that's a time killer and it's like not worth doing, but I didn't know what the hell to do here.
Oh, it's just my pen that wasn't working. Okay. Okay, let's see. Carbon 14 labeled mevalonic acid compound. Oh, this is from a passage. Compound 2 produced from C14 labeled acetyl-CoA. Reactions 1 through 3 is converted in vivo into that. Compound 3. Okay. What is the expected C14 labeling pattern found in in compound 3? Okay. Wait. Compound 3 is isopentenyl pyrophosphate, and they're asking for isopentenyl phosphate. Okay. Let me see. Like the
Can we go to the reaction or passage? I think it started here. I don't think it said much up here.
Okay. Okay, so that asterisk. Okay, so that two acetyl CoAs. Okay, then it's there and there. So that's carbon 1 and carbon 3. Carbon 1, carbon 3. And then they add it to an acetyl CoA. Okay, then they stop talking about. Okay, so then they stop like telling you where it's labeled. So let's see. I mean, these two seem. Wait. Okay, so it should just. Okay, so it'll connect onto that. Here, let me see if I can do this.
All right, this and this. Okay.
I love how they adapted this from a biochem textbook from the 70s.
I have the same one, but not from the 70s.
Not that
The
same book, but it's
Lenin,
not from the
Leninger
70s.
one.
Yeah. Yeah.
Okay, so I think yeah, I think I get it here.
Yeah, I didn't know where to start. I'm like, I'm gonna waste a lot of time. So basically, you're trying to follow the carbon.
Yeah, here I'll share my screen.
Yeah, sure.
So it seems like, whoops. So okay, from here to here, it seems like there's this S-CoA leaves, and there's a bond made from this carbon to this carbon. So that's that red line there. So it looks like this.
Okay. Yeah.
So
that forms that. Okay.
Yep, and that's labeled and that's labeled. And then here, it seems like this, so like that S-CoA leaves again, and then a bond is between this carbon and this carbon over here to make that. And then there's this enzyme step over here with H2O, which the H2O binds to like the partial positive carbon here, which causes this to turn into like O minus, like this. Like that's the H2O, and this is the O minus. And H2O is a good leaving group, so that leaves, and one of the hydrogens, because it has an extra hydrogen over here, like positive, so it goes here to this O minus to turn into an OH group over here. And this is still going to have a positive charge here, which means that it can undergo an alkyl shift, which means like an alkyl group, just like a CH3, can move over there. So that's what we have here. Like this and this are supposed to be the same, but this CH3 jumps over here, and I think this oxygen over here is just from like this thing, I think, like turning apart. Let's see. So okay, so over here we have this, and this being what's still labeled. Like this is that right there. So like here, so like I labeled it with like A, B, and C so we can keep track from one to the next. So this one is A, this over here is B, and this over here is C. And here, this one stays, so that's A over there.
Yep.
The hydride shift happens, so this B goes here. So
I
that's
see that.
B over there. And then this C is what attaches to this over here. So that C goes over there.
Okay.
All right. So
that's what we have here as well. And then this happens, which basically, that basically gets rid of like this entire group over here and leaves it as like an OH. But nothing's happening with, like, we're not adding any more C14 like labeled, so it still stays the same over here. And then over here, then they add, then some carbons leave as CO2, but it's just the like this CO2 that is settle or whatever, this thing leaves the CO2, so that leaves, and it just leaves it as like a double bond. So like this entire thing leaves, so just this, that, and that, like right there. So so that's carbon 1, this is carbon 2, carbon 3, carbon 4, and carbon 5, I think. Yeah. So, yeah, this is like, so like I would just start from here, see that this thing leaves, makes a connection to make that with those two things labeled. Same thing here, this makes a connection here. The weird thing is just like how that B goes from over there to here, and that's just because of an alkyl shift. So then you just have, this, and that. And that stays the same pretty much all throughout it. But in this last step where this carbon, this like CO2 leaves, like when it leaves, it's going to like be like, a negative charge, and that negative charge is just going to enter in to make like a double bond there. So that's kind of a hard one.
Yeah, my organic chemistry teacher would have gotten this wrong.
Yeah.
I'm sure they would. I'm curious who the hell writes these questions. Like, some of the stuff is.
Yeah.
I mean, I know what they were asking, but I'm like, that's gonna take me a long time to try to follow.
Yeah.
I'm still at the 2, 4. So I guess I was just supposed to follow it through from the start.
Yeah, it gets weird in reaction 2 where there's that alkyl shift.
And they kind of flip.
Yeah.
I honestly don't. It would take me a long time to really understand.
On the actual test, like this is one of those ones that you like just guess and flag.
I just don't understand why they include questions like this. Like I took some upper level classes too, and like I don't see how people will get this right on the test. I mean, unless you're good at guessing, like that's just a real time killer.
Yeah.
I mean, you would have to start. Yeah, I'm just gonna I might go back and read over that again and go through it and try to understand the flow on my own time. But I just think that's a lot. This passage was pretty rough too.
Yeah.
39 or anything. 50-50. Yeah, Fisher esterification. I knew it was going to be A or B because these structures didn't make any sense. Mevalonate exists in equilibrium with compound X in aqueous solution. What's the structure of X? I didn't know how to get to this, like, at all.
Oh, yeah. So I guess the OH group. So, like, you see compound 2? Yeah, that OH group. Yeah, whenever you see an OH group, it's a strong nucleophile. So it's going to attack the partial positive of the carbonyl.
Here?
Oh, yeah. No, the carbonyl.
Oh, here,
yeah.
Sorry.
That has like a partial positive towards the carbon, partial negative towards the oxygen. So the OH group is going to attack that.
Wait, so isn't this this double bond going to become a single bond? This kicks off. Like here, this comes through backside attack or whatever. the OH, here.
Yeah, that thing, attaches to that. This thing turns into like the O minus thing. So that's like the ring over there. So that's going to be 1, 2, 3, 4, 5, 6. Yeah, it'll be a 6 ring structure with oxygen part of that ring because of that OH attaching to it. So that means we can rule out C and D.
I just didn't know how to figure out for sure. Like, I didn't draw anything on my paper or anything, but like,
Yeah.
I wasn't 100% sure how you knew if it was going to be a double O here or if it was just going to be a single OH. Like, I didn't know.
Oh, okay. So let's see.
Yes, you could think of
that, and that thing will go back and turn into an O minus, and
Does it have to do with this would be deprotonated?
Yeah, that'll be like deprotonated and added on to like the O minus to make. Wait.
Because like the answer isn't the answer A, so I just thought. I guess I was looking at this, like I wasn't sure. Like that still shows the alcohol on there, and this one just shows this forms the double bond. So I wasn't sure.
Yeah, okay. The H leaves, it attacks that becomes O minus. There's going to be 2 O minuses. Let me see how that makes sense. 2 O minuses, equilibrium of compound X in solution with the structure of compound X. OH or double bonded O? I guess like, okay, since, that double bond in the carbonyl, like, jumps to the O to become a single bond and an O minus, one of those oxygens is just going to go back and make the double bond again. So, like, it's either going to be the one that's a carbonyl at the beginning, or that oxygen that's an O minus there. The negative is just going to be going back to make a double bond.
Okay. And I think I copy
And I
paste
think one of them
stuff
just
to-
leaves.
Yeah, I copy paste stuff to Google, and they were talking about lactone. So I think I wrote on the side there. Where did I write it at? About the Fisher esterification. I don't remember what number this was.
39? Yeah, you said
Yeah,
the Fisher esterification that forms the lactone.
That's what I saw online, and it kind of talks. I mean, they didn't really explain it well here. But that's what somebody said.
Mm-hmm.
I don't know that mechanism really. I mean, I know they.
Yeah.
I mean, they gave it to me or whatever, but like, you shouldn't have to draw out stuff to like. I can't like visualize them together always that quickly. Like sometimes it's easy to identify things. Like obviously, I knew it wasn't gonna form this type of a ring structure. Like looking at it and the carbons and everything, I knew this was gonna be it.
Mm-hmm.
But I guess I just couldn't determine for sure whether the alcohol was going to be there, if it was going to,
Yeah, I'm still trying to.
I guess I see the double bond. I guess that's not just going to go away completely.
But like one of the oxygens leaves though. Like you start off with 1, 2, 3, 4. You end up with 1, 2, 3. So one of them definitely leaves. I guess as like H2O or something. I'm not really.
I mean, I guess I could play around with it with the
yeah.
try to figure out the mechanism, which they don't show you here in the answer solution, which is really nice. Like, I don't understand why they just assume you know this stuff and they don't explain it. I mean, that's what's really frustrating with the AAMC is like I don't always understand because they don't explain it very well, and then people on Reddit don't always explain it really well.
Yeah.
I mean, like I'm looking at the OH here. What do you use to pull off?
So my guess is that
when you want to pull the proton off of the H.
Yeah, so when it attacks the carbonyl carbon and makes a bond with that, it's going to be like an OH positive or whatever. And so like I'm going to guess like that proton's just going to go to one of like the other O minuses cuz why not to make like a but it'll have to there has to be some type of leaving group. Oh wait. Okay. Yeah, because when it attacks that, it's going to be, so the oxygen is going to be bound to a hydrogen, bound to a carbon, and wait, oxygen. Okay, so the carbon, the ring thing on that it's already attached to, so that's a carbon. It'll be bound to the carbon of the carbonyl, and it'll already have the H there. So I guess when the thing comes back, it's just gonna lose one because it's just too many bonds. But yeah, you can like play with that exact. I'm still not sure exactly why it's the double bond O instead of the OH.
Yeah, that's my problem. And I guess apparently this mechanism, you're supposed to just know that. But like, I mean,
I think it's like an SN1 maybe or something. I don't know. Because there's one of the things leaves is H2O. I'm certain of that.
I think this is leaving.
No,
right?
that's the one that incorporates
Don't you want to
itself.
don't you want to deprotonate that first though to make it?
Oh, it gets deprotonated, but that thing becomes the O that's in the ring because that O attacks the carbonyl and forms a bond with that carbonyl carbon. Yeah.
I guess I'm confused. Aren't these electron? I mean, the air. I'm trying to think of the errors. Like, if that would go up there or not?
Yeah, it would. It would. Like when that OH on the right attacks and makes a bond with that, that double bond's gonna go up and it's gonna make an O minus. So there are gonna be two O minuses. One of the O's leaves completely, and I think that. Yeah, I
don't know if we would use like NaOH or something to pull. I don't.
Yeah.
Well, I've seen like I know what they're getting at. It's just like in 30 seconds you're supposed to be able to answer this. And it's like, well, it's gonna be I'm 50-50 here.
Yeah.
I'm like, I don't know if this is we're gonna have an OH. I don't know if that's gonna lose. I guess I could have thought in my head that would probably at some point get pulled off.
Yeah.
When it was included. Well, I guess you were saying though that that's included in the ring.
Yeah, that's included in the ring.
Something's happening over here, and yeah.
So
all right.
so if you knew that it was a lactone, like I didn't really remember that. Lactone is a ketone, so that would make A true because that has a ketone group in it, and B has an OH
didn't
group.
know. I mean, I knew,
but
that.
But
was,
yeah,
I
don't remember that it's that it makes a lactone.
I knew this because I had memorized my absorption stuff.
That's good.
That was good. What was this? What question was that? 41. No clue. How was I supposed to know the enzyme was chiral on a road because acetyl coenzyme A is not chiral? All right. What factor explains how a single stereoisomer is formed in reaction to?
Reaction to, okay. Oh yeah, so remember like enzymes are super specific. So yeah, you're right in knowing that acetyl-CoA and stuff are not chiral. Like none of these things are chiral until like after the enzyme 1. Then you just have that one chiral like one. Like, yeah, you're right in acetyl-CoA is not chiral. So the only thing that must be chiral or stereospecific is the enzyme.
Yeah, I think I just guessed because I didn't know what the heck was going on.
Yeah.
Okay.
Yeah.
I mean, I never even thought of enzyme in terms, I guess enzymes are proteins. I never really thought of the enzyme in terms of chirality, in terms of anything I've learned about chirality.
Yeah, it's because like they're stereospecific, which means that they operate, like they can distinguish between something like that's an L or, whatever, an R isomer.
Okay. Yeah, I didn't know how to do this one.
I think I mentioned this a couple of times with the optics.
Yeah, I need to go over that more in depth maybe one day with you. I just
Yeah.
I hate it. I knew it was converging or diverging.
The optics the optics Reddit post that I made. Yeah. I whenever I talk about optics, I always bring bring that up. Here. I put the link in here. But yeah, basically myopia, like nearsightedness, is your eyes are too long. So it converges in front of the retina. Yeah. So, that's that. And then I talk about it like underneath that. Yeah. So, and then you can see like in the pictures. Yeah, like myopia basically means that your eyeball is too long. So see how it converges prematurely? It converges in front of the retina. So you want it to converge less. So you put in a diverging lens in front of that. And then hyperopia is when you're, farsighted, which means that your eyeball is too short. So it converges too late, like behind your retina. So you need to have it converge faster or sooner. So you put in a converging lens to make it converge more.
Okay.
Yeah.
I was thinking that I didn't have like a visual for what that looked like, and I was thinking like
Yeah.
I was thinking that it would converge. So I guess
it converges too soon. So you need to offset it with a diverging lens.
Okay.
But yeah, I talk about it in that post. Because the post started off just going over optics, but then, I figure it's a good opportunity to incorporate like the, like eyes and stuff as well for questions like exactly like that.
I'll go through that as homework. So it's time for like one more. This one, Let me see what I wrote here. I got this one wrong. Yeah, I knew. So one method of isolating polypeptides and proteins from aqueous extracts is freeze drying. The aqueous solution of the polypeptide or protein is frozen. What procedure can be used to remove the water from the frozen sample? I didn't know why D would even be true. Extraction. I was just trying to think of this is kind of like a lab methods question. Extraction with organic solvent. I didn't know. I didn't think of distillation. I guess I was thinking in terms of distillation, being able to separate it. But the reason that was wrong, I guess, is that distillation would maintain the native protein structure because of the heat.
Yeah, because you have it like freeze drying, so it's okay. So basically, okay. So let's see. It's frozen, and you want to just remove the water without making it, but you need to keep the protein frozen still. And distillation using steam will make will add heat and crap to it, making the protein no longer frozen. But sublimation is when you basically take a solid and you turn it into a gas without going into that intermediate liquid step.
Yeah, I think I forgot what sublimation meant. Like the other ones, I had remember. I forgot what that one meant.
Yeah, sublimation is when it goes from solid to gas without the liquid. And the opposite is deposition, where it goes from gas to solid. But the idea is that we want to get rid of the water, but we want to keep the protein frozen. So sublimation means that the frozen water, the ice, just turns straight up into water vapor and leaves.
Was it deposition? This is from that graph, that chart.
Yeah, like phase changes and stuff.
Yeah, phase changes. That's what that was. I think it just those terms. It's sublimation, deposition. I get confused what they mean. The other ones make more sense.
Yeah.
All right, cool. All right, that was. So I guess next time maybe we can finish these and go through the bio questions, which I also did pretty terrible on. I just feel like this was a really hard. Like some of these were simple, and then some of these were like really hard.
That's true.
All right, I'll try to go through I want to take another practice test. I'll take the FL1 this weekend, and I'm going to try to tomorrow. So Saturday and Sunday, I'm going to have to spend all my time doing that and reviewing. I'll try to go through the optics and the things we talked about.
Yeah.
But like, I'm just a little concerned with these sections, the bio and the CP. Like, I feel like I've improved a lot, but I also am getting a lot of stuff wrong. And a lot of their questions, at least on the sample, which maybe feels kind of hard, like I don't see a way through some of those questions. I don't know. It's just tough because I reviewed a lot of content and it really didn't pay off.
Yeah, I think you'll be. Yeah,
And knowing the content, I was getting stuff wrong, just making assumptions or thinking I knew something, they meant something else. So like, I don't know what you're saying my issue is. Like you see, I think pretty quickly, I'm usually 50-50.
Yeah.
And I did get, some stuff right pretty quickly, but then I was getting stuck a lot.
Yeah. Yeah. It's the AAMC stuff is going to be like really tricky in that way. But you know, the stuff that, I would like kind of, because the stuff that I noticed you were getting wrong, like kind of had like the stuff in the passage, so it was a lot more like passage intensive than a lot of like the actual like practice tests are, because the actual practice tests are kind of like, you know, you could just you could look at the question and then look for where the question, like where the relevant terms of that question are in the passage. But for the ones that we went over today, it's like the entire passage came into play, which is not usually how it is, but sometimes it can be like that. But those are pretty.
I was really frustrated taking this one because I felt like it was constantly like, what the freak's going on?
Yeah.
It was like going in circles or like I would feel like, oh, I got this right, let's move on, and I needed more stuff because normally I thought this was harder than the section banks.
Yeah.
I just felt like they were tough, or maybe it was that they were testing a lot of weaknesses, but I did better on the biochem, but I still got a lot wrong. So I guess we'll keep going through it and figure it out. But I feel like I'm on the right track. If I can keep up with the psych, soc, and the cars, if I can get these up a few points, like I'm not too far off. A good score. So, all right.
Yeah.
And I'll email you my schedule, what days I have off so far.
Okay.
And we like my current schedule, like times we can try to meet and try to get as much in as we can so we build up to this test.
Okay.
Oh, cool. All right.
All right.
Talk to you later.
All right.
Thanks.
Take care, man.
Bye.
All right, bye.